Can you hear me?
Yes, I
Oh,
can
good.
do a quick introduction and then you can get started. I think use that. Yep. Uh, Hello, everyone. Welcome to day 4 of the LoG conference, and thank you for your participation so far. Today, we have a keynote speaker to kickstart the day, and I'm very thankful to Dr. Alden Hung, who is a principal research scientist at Isomorphic Labs and a core contributor of AlphaFold 3 to actually deliver a keynote on this very topic. Dr. Alden Hung actually has a background both in neuroscience and in computer programming, having won many competitions along the way, and then having gotten his PhD from Johns Hopkins and then a postdoctoral fellow from the NIH. About 9 years ago, he moved to DeepMind to work more on reinforcement learning, and now he's set his sights on drug discovery with the AlphaFold team. Without further ado, I will let Dr. Alden Hung take over from here. Thank you for giving a talk here.
Thank you, Vignesh. Hi, everybody. I'm Alden Hung, and I'm representing Isomorphic Labs today to present our work toward rational drug design with AlphaFold 3. So at Isomorphic Labs, our goal is to advance human health by reimagining drug discovery with power and pace of artificial intelligence. And in this very example today, I'm going to show how AlphaFold 3 is actually being the main driving power in Isomorphic Lab in the last few years. So how can we use artificial intelligence to redefine drug design? Here I want to just give a little bit background. We know we all love the exponential growth of the technology, right? We know everybody here is very familiar with the Moore's law. Things are getting faster and faster on our hardware side, and our GPU performance are getting just exponentially grow as well. And on the other side, things are very different in the drug discovery industry. So you can see on the upper left-hand side, if you can see my cursor here, you will see this is the drug approved every year. And you can see it's not a big amount. It's only on the handful of scale of dozens of drugs being approved every year. And the cost of each drug going to the market is just getting more and more across the year. So there is a law called Eroom's law, which is like the reverse of Moore's law for the drug discovery industry. It's saying it's getting more and more expensive exponentially to get the new drug into the market. So can we use artificial intelligence to make this getting better? So I would quickly introduce you to the bottlenecks in the drug discovery. So on here, we see a standard drug discovery pipeline looks like. From left to right, the starting phases we call target discovery and target validation, which is more on the biology side. This is identify what is a protein or what is the molecular target that we should be aiming for to making the intervention. And then on the middle of this is the chemistry side that we call hit identification and lead optimization. This is once you identify the target, how would you find the molecules that can be interacting and intervening with the target protein? And then later stage, there is this preclinical and clinical trials. And there are various bottlenecks here, which I will focusing on bottlenecks 1 and bottlenecks 2 today. The bottlenecks 1 is understand the disease biology. So potentially, can we use AlphaFold to understand the biology better? And also, even more importantly, can we use AlphaFold to help us to design better molecules? So this is the bottlenecks 2. And there are other bottlenecks, but I will focus on 1 and 2 today. So one thing I would like to emphasize is structural prediction. Structural biology is a key enabler in drug discovery. There's two parts of this. The first part is the structure prediction make us to have a better understanding of the biology. So for example, in this particular example, we are seeing how the protein is interacting with the DNA here. So we can know what is the function looks like. And also more so, we can also use the structure prediction to help us doing this we call the rational drug design, which means if we understand the 3D structure of the target protein, like here, this is the gray area here with this cavity is a protein with the empty space we call the pocket. And you can starting from a small part of this ligand, which is a small molecule. you can gradually grow it into a bigger part and eventually growing into a full drug-like ligand that is binding to this target protein and stopping intervening the function of this protein. So we have this latest model, AlphaFold 3, published earlier in the year, which is a joint collaboration between workers from Isomorphic Lab and Google DeepMind. And this is a gradual work that building upon from the legacy of AlphaFold and AlphaFold 2. And this new model is able to predict structure of not just protein, but also DNA, RNA, and very importantly for the drug discovery, the small molecules. And technical-wise, this is a diffusion model, and this is getting to the new state of art across all these different metrics. And I will next go into deeper about the details about how AlphaFold 3 is making this to work. So overview of the AlphaFold 3. So let's start in reviewing what is AlphaFold 2. AlphaFold 2 is the first foundational model for biology, and it's work in the way that given a sequence of amino acid, as you can see on the left, it's just like very simple. It's just like a string of characters. This model is able to generating the 3D coordinate of every single atoms of this 3D protein structures from just like this sequence. And the way this is working is actually it can also use the genetic database search, which using the multiple sequence alignment, which is a very important information also for folding the protein. And this is AlphaFold 2. The limitation is that this is only working for protein sequence, and this is actually also only working for a single protein chain. So over the year after AlphaFold 2 first released in 2021, the next year after my colleague also released AlphaFold multimer in 2022. And the difference, the extra advantage of AlphaFold multimer is that it's able to fold multiple protein chains, as you can see in this middle page. And just earlier this year, we published AlphaFold 3, which, as mentioned earlier, this can fold all different kind of biomolecules, including DNA, RNA, protein, and every possible small molecules. Just as long as you can provide the molecular graph, we can fold it. Okay, so a very high level, too long didn't read. AlphaFold 3 is a diffusion model. AlphaFold 3 can fold this different kind of biomolecule identities. AlphaFold 3 produce better result in protein ligand co-folding, better than the classical docking algorithm, which I'll talk about more in details later. It also gives a better protein-protein folding prediction, especially it is reaching much better result in protein antibody antigen interaction compared to AlphaFold 2. And this is also working very well for nucleic acid folding. So this is an overview of the model of AlphaFold 3. I will not try to actually go through each single block on this page, but I will try to showing some high-level ideas about how the model is working in the next few slides. So first of all, the model is taking input as in AlphaFold 2, but now besides the protein sequence, it can also taking different kind of modality of input. For example, here there's this ligand molecules, and also it can also taking input as DNA and RNA. And basically, this is a conditional generative model, and this is a diffusion model to be specific. And the conditioning actually goes through like this. So the input to the model going through a featurization, and this also including with each protein or DNA RNA sequence, we will do the multiple sequence alignment, and that will be the extra information into the model. And then there will be this trunk part of the computation, which will generating a trunk embedding. And this trunk embedding will be the input to the diffusion module, where the diffusion module is the head part of the module that is doing the diffusion kind of generation. And also very interestingly, which is that we also have a confidence head. This is something we already have in AlphaFold 2, and it's also still very helpful in AlphaFold 3. This head is taking both the embedding from the trunk and also the sampled structure. And the job of the confidence set is to predicting how well is the model's generated structures are. So it can give the user a sense like how confident the model is. And I'll get in more details about how this confidence set work later. Okay, so in comparison of AlphaFold 2, I just want to highlight, if you are familiar with AlphaFold 2, what is new from AlphaFold 3 and why it is working better. So this is a diagram from the AlphaFold 2 paper. And basically the main change is that we replace the middle part of the model. It was used to code Evoformer, and we replaced from a simpler and more kind of uniform architecture called Pairformer, which I will mention in more details later. And the second part that is also quite important is that we replace this very complex structure module, which doing some kind of very fancy equivariant computation with a much simpler diffusion head. And it's turned out it's working quite well. Okay. So one thing I would like to get into more detail is like, what is the computing unit? What is the token, or how do we featureizing the information? So this thing is kind of like a language model with tokens, but it's actually more like a graph, but it's a fully connected graph. So we have a sense of a token, or each token you can also think as a node in a graph. And what is the token in this AlphaFold 3? It either can be a residue, so it can be a chunk of atoms in standard protein, DNA, RNA. Is, for example, as you may know, DNA and RNA have this standard vocabulary of ATCG, and there's also 20 standard amino acids for the protein. So in those cases, you can encode things at more compact way. So each node will be a single residue. But for a general ligand, for any general molecules, you cannot use such kind of vocabulary anymore because there are a vast amount of different molecules. So in that way, we decided the best way is to just encoding things at a single atom level. So in that way, it can express any possible molecules. So you have this kind of hybrid description. Some nodes are presenting a larger chunk of the atoms. Some nodes are presenting a single atom. And the way the computation is working is actually saved as like a 2D tensor. So it's like number of node by number of node by channel. And the computation is happening on this 2D tensor. So one way to think about this is a fully connected graph, and we are doing a lot of computation on this fully connected graph. Okay, so just to give an example, what do I mean by a residue can be a standard protein? That means, for example, if this is a glycine, then that which is the standard amino acid residue, then this token will have multiple atoms positions. But if it's a ATP, which is a very common molecules in the body, then because this is not a standard vocabulary, this will be, we call flatten out, this will be represented by each one token is one single atom. So this ATP molecule is of like 30 something atoms, it will lay over 30 something of the tokens in our representation. Okay, and now let's move on to the featureization. As I mentioned a bit earlier, we get all this input, the sequence, the ligands, and other information. And this will go to some further computation. We will do some template matching, see if there are some template you can retrieve from the database to help you do the prediction. And one very important information sources is this thing, genetic search, which will give back the multiple sequence alignment, which will be a very strong and helpful signal to help you know which two protein residues are co-evolution and they may be in contact with each other. And for the molecules, we can generating the floating, free floating conformers. And this can be good reference signal about how those molecules should look like, and we can fold those together with the protein. So this is how we featureizing the input. And then let's go to the trunk, the part we call Pairformer. And this is the detail of the Pairformer. It's doing two types of computation. One is the triangular update, which is updating the input and output of a particular node, say every signal flowing into the node and every signal flowing out to the other node. And there's also the axial attention, which means because this is a very large 2D matrix, we are not able to do a standard like transformer kind of attention with all these n-squared tokens. So we'll choose a subset of token, like every single row or every single column, this subset to do the attention. And this is being repeated for multiple blocks. This is basically just a simplification from the evil former, if you are familiar from that term in AlphaFold 2. And then now we get down to the diffusion module, which is a head upon the trunk part. The diffusion module is getting the noise ground truth, or in the inference time, it was starting from random Gaussian noise. And so we're taking the input from the trunk, and this trunk input will be the information to guide the diffusion head to denoising this noisy input into the ground truth target. And this is trained with a standard diffusion model training. And one thing interesting to mention is like, we are not doing any kind of equivariance diffusion. In here, we're just doing something very simple. We just randomly rotate and translating the target thing with this data augmentation, and it's turned out to working just quite okay. And the losses for the diffusion model, there's the first part is the mean square error loss on the atom coordinate. So this is the standard diffusion losses. You're just denoising your current noisy input to the target, and then you computing the MSE. And we also have other part of the losses which turn out to be very helpful, even though they may be like fully mathematically grounded, but these are the like extra weighted for the bounded ligand to make sure they are in the correct location. And we also have a LDDT loss, which means we care about the distance between pair of the atoms. Okay, so now we'll move on to the AlphaFold 3 training. So the full training loop is like this. We have this network, and we have the diffusion inference here, and we have the ground truth here. And with the ground truth and the denoised output from the diffusion model, we are computing a loss. This is the loss I mentioned in the previous page. So the mean square error loss is then other two losses. And also the other part of the loss is on the confidence module. So we have the confidence module that will be able to predicting itself. It's reflecting itself on how well is the generated molecular structures are. Okay, and this has three different parts. It's have the PLDDT, which is already in AlphaFold 2, and also have the two other terms, which is quite similar to each other. It's predict distance error or predict align error. Both of them are just estimating. Can you tell me how much is the error for predicting the distance between two tokens? Okay. So here we show a little bit how the training looks like. The training takes about on the scale of like 2 days, and then we do some extra fine tuning. And in the fine tuning stage, we increase the crop size. So one thing we need to do for training the AlphaFold model is that we need to crop the input data, because the data set we use, these biomolecules are sometimes can be really large. So they can have like on the scale of like several thousand tokens. But during the training time, we cannot fit in with such big token with our current hardware. So we need to crop into smaller part. And it's turned out this works really fine. We can always just learning from part of the input structure. It's like you learn from part of the image. And this generalize okay when we are inference on the full structure. And basically the main thing is like we adding some extra losses on this later fine-tuning stage, but most important thing is that we also make the crop size bigger. And on the right-hand side figure here, you can see this is how different metrics looks like. So everything here, the y-axis is the LDDT, which is a way we measure the quality of the structure. And this is for different kind of entities. So for the ligand, intraligand is getting to a higher value and plateau like quite early. But for some other metrics like protein-protein interaction, you can see this actually converge much slower and actually getting this benefit from the fine-tuning with the larger crop. So we have a like weighted sum of all these metrics that help us deciding when is the best time to save the final model. Okay, one thing that I've been mentioned very quickly in the previous page about the training loss, which I want to highlight further again here is this permute ground truth. This is some detail about training the model, but I think it's quite interesting to mention. It's like this particular block here is a permute ground truth, which is actually quite important and a tricky part to deal with in the AlphaFold design. So the idea here is like when you are generating the correct, like generating your samples, how do you matching your performance to the target? And in this particular example, 10GS here, there are two identical chains. We call it the A2 homomer. And there's also two ligands here. And when you're denoising and generating your target, you need to permuting your answer to your samples to computing the correct loss. You cannot just say, okay, I'm just assuming my generated sample one is matching to target one. You need to run all the permutation. And the same permutation is also necessary for the small molecules. For example, in this particular molecules here, you see like there is a benzene ring here and with the oxygen here. And with this atoms 0 to 5, it will be the same in these two different permutations. So one need to be very careful about when computing the losses, like it's considering all the possible permutation and computing the loss correctly. Okay, and now I'll move on to share some of the AlphaFold 3 results, which is probably the most exciting part. And this is a full summarized page about how the model performs on the ligand set, on the nucleic acid, and on the covalent modification, and on the protein. I will go into each subcategory in the next few pages. So first, let's focusing on the protein ligand. In this category, we rely on a dataset called PostBuster, which is a third-party paper. Like there's this particular dataset. And here we compare AlphaFold 3 with a few other also like recent coming paper, like for example, Rosetta Fold here, and also a few other approaches, diffdock and some other method, and also like some classical old docking method like VINA or GOAT here. So, and the y-axis is here, you can see is percentage of RMSD less than 2 angstrom. This means like how well you can put the ligand correctly in the protein pocket. And the blue bar is the performance of AlphaFold 3. You can see it is performing very well. One thing I want to mention is like AlphaFold 3 is essentially very different from all this classical docking method and some of the machine learning method like diffdock. In the sense like this method, they assuming you already have the protein structure. And your degree of freedom is only how you put your ligands within this already rigid protein structure. But AlphaFold 3 is doing a thing we call co-folding, which means we are generating both the protein structure and the ligand together. So potentially this ligand, this protein can actually, is there a question or no, sorry. So potentially this is able to actually generating a protein with ligand that say when you fold this protein by itself, there's a cryptic pocket. So this pocket actually closes up, but only when you run the model together with protein and ligand, you will see like this ligand going to the pocket nicely. Okay, so this is performing really well. And as you can see here, we are overlaying the model's prediction and the ground truth, and you can see they are overlaying very well, which I was showing more details, more examples later. And one thing I want to show as a highlight or as a like things for future work is like you can see these are a bunch of different quality control people do in the PostBuster benchmark. And there's like two things I want to highlight that the AlphaFold 3 is not doing perfect yet. The first one is this tetrahedrochirality. This means like when you have a molecules and you have a atom in the molecule that is bonding to 4 other atoms, there is a thing called chirality. And do you get your molecule to have the correct chirality? And we can see the AlphaFold is doing okay, but not perfect. And some other approach like DiffDoc is actually by construct doing this perfectly. So this is something we are trying to improve. And there's also this intermolecular validity. This is like the distance between protein and ligand. This means like when you fold this structure in your prediction, do you have any collision between your protein and ligand if you put them too closely to each other? And AlphaFold is not working at 100% here, but very close to that. And the performance on DNA and RNA, which is this like new features we can do, it's performing really well, I would say, in general, and performing very well. It's not better than this approach called Alchemy RNA2, which use a human input. But as a pure machine learning approach, this is the state of art. And as you can see in this example, it was able to nicely fold this DNA along with this protein and give a very reasonable confidence predictions here on the right. I will explain a little bit more on what the confidence prediction means later in a slide. And here I want to also highlight an other new feature in AlphaFold 3, which is not in AlphaFold 2, is this covalent modification. So in the protein, there is a thing called post-translational modification, PTM, which means usually you have this 20 standard amino acid residue. But sometimes after this protein getting generated, translated, they will getting modification. For example, there will be like one extra phosphor being putting onto the residue. And in the original AlphaFold 2, we were not able to modeling that. But in AlphaFold 3, we have an approach to just treat it, this modified residues as like a ligand. So we have a way to handle this kind of molecules. And in here, you can see we have a specific amino acid residues here, which it correctly should be this thing called SEP. And the standard one will be this SER. And the difference is like in among these two, as you can see, the difference is having this extra phosphor groups here. Okay. And AlphaFold 3 is able to correctly modeling this change. And this is actually a key important thing to model in this particular example. If you are not modeling that one, then you are not able to correctly putting this peptide into the correct position. But while AlphaFold 3 can actually modeling this complex well and putting the thing in the correct place. Okay, next. And finally, I want to show this protein-protein interaction interface prediction. This is when you have like two or more protein chains, which you want to model how they are interacting with each other. This is in general much harder than folding a protein chain by itself. So this is a harder task. And one thing particularly interesting is here is that we can actually modeling much better in this antibody antigen interaction. And the way that we can actually do this well is that we can actually run the model multiple times. So you can actually scaling at inference time. What we do is that we just making multiple seed, like running the model multiple times. And each time the model will run with a different subsampling of the MSA. And the key thing why this work is like because the model have this confidence head. So it can use the confidence heads to choose among this like 1,000 generated samples. And it's actually indeed can use that. So it's actually can scale. As you can see, when we're getting more samples, we actually can get a better performance metrics. And then this is just an example showing we are able to fold in this particular case an antibody with the antigen. Okay, and finally, this part is about the confidence metric tracking the accuracy. This is showing, again, the importance about this confidence metric, as I mentioned earlier in this antigen antibody folding. The confidence is a very important and very useful information for the chemist to look at the structure. So for example, when we folding these particular structures here, this structure are 4 different chains, like one in magenta here, one in orange, one in blue, and one in gray. And this predicted distance error matrix is showing how confident are you about different part of the chain. So for example, we can see there is a high confidence within chain, which is not surprising, right? So because as mentioned earlier, it's always easier to fold the chain correctly. But the more interesting thing is like we know also here the darker gray means like better confidence. Okay, so here the model tell you, okay, I'm very confident between chain A and F, and I'm also very confident between chain C and D, but I'm less confident between the relationship between chain AC or AD. And this is actually quite makes sense because this whole complex is floppy in the middle. So this upper and lower half can wiggle it around. So that's why the model correctly suggesting it cannot be very confident for those two chains. Okay, and with all those description about AlphaFold 3, I now want to move on to share a little bit about on the application side, how in Isomorphic Lab we are using AlphaFold 3 to enabling our rational drug design. And one thing very important is that we want to make sure this is working on novel target, working on novel protein ligand interaction. We don't want to have a model just memorizing the data set. We want to make sure this is actually generalizable to new protein target that we actually don't have structure. New molecules is not being designed yet, but our model are still be able to predicting the structure with this novel protein and novel ligand combination. And we are actually using our model in the day-to-day discovery pipeline in Isomorphic Lab. Okay, in this first example here, we are showing this is a novel target, not in the training set. And in this kind of protein target, there's usually more than one pocket. That means if you fold a ligand with this particular protein, it potentially can go to different places. And in this particular example, we can correctly fold this target into folded this ligand into the correct pocket with respecting to this protein, which is not in the training data. And then here I would like to show you a short video about another example of how we use the model. Oops, sorry. So here, this is an animation of a protein target called TIM3. And we are folding this by itself now at the moment. And you can see now we are folding a particular ligand with this. And as you can see, when we're folding this, the blue part is the ligand, and the orange part is the side chain from the protein. And you can see whenever we fold a different ligands in, this protein part slightly changes. So this is what I emphasized earlier. What we do is a co-folding. We are not keep the protein rigid and just putting the ligand on it. So this is actually making it possible for the whole complex to find the most low energy, most plausible state. So it's not like you have a rigid protein you fold first and then you just dock your ligand on it. Okay, move on to the next page if I can. Sorry. And here I want to highlight another very cool example here. So this is a very complex ternary structure. As you can see, this is a really complex thing. There are like two protein chains here. And here, the way it is showing is the white is the ground truths and the blue and the pinks are the structure prediction from the model. And as you can visually see this, they are basically looks like overlapping super well. And this is quite complex because this is a structure where you have two protein chain and there is a ligand standing in the middle that is interacting with both sides of the protein. And we were able to fold this very well. And one thing I would like to highlight with this particular example is that we are actually able to use the confidence matrix to correctly selecting this best folded result. So in this lower right scatter plot here, the x-axis is the quality of the result, the protein ligand pocket RMSD. So lower the better. And the y-axis is the confidence score. So you can see we're generating a bunch of different molecules, a bunch of different predictive structures. Some of them are better than others. But the top one, the most confident structures by the confidence metrics score is actually indeed the one with the lowest RMSD. So this is a really nice example, our confidence metrics helping us to selecting the best possible samples. Okay, so we also have this AlphaFold server, which is publicly available for everybody to use. And this is a server launched by our colleague at Google DeepMind. And you can find this on the internet and feel free to leave a feedback. And I think there's a lot of people actively using this web server. And also we have the GitHub code that is able for academic use, which you can find here on GitHub. Okay, let me now quickly go through some kind of not fully solved area and the limitation of AlphaFold 3. Okay, the first is the conformation coverage. This is actually a quite interesting one. So in this particular example called cereblon here, we have two structures we call apple and hollow state. Apple state means you only have the protein by itself. And the hollow states means you have the protein together with a ligand. As you can see, if you look closely, there is a ligand here. Okay, and you can see this is a case where the protein is taking different, the silver one on the left-hand side is the ground truth, and the blue is the model prediction. And this is a very hard example because this is saying when there is no ligand around, these two sides of the protein, they are far apart from each other. But when there is this ligand coming in here, this kind of like close up, and this part is taking a different conformation. And the current AlphaFold 3 is not able to modeling that correctly. It's actually modeling the part when the ligand coming in fine, but even when there's no ligand, it's still generating this wrong state. So this will be something to work on in the future. And the other thing is this hallucination, which is a quite tricky thing, and this is happening with the diffusion model in AlphaFold 3, which is less a problem in AlphaFold 2 before, because we have other losses to handle with that. This saying, if you have a protein where your ground truth is this particular part, so then this one is the ground truth, and you can see AlphaFold 2 and AlphaFold 3 are modeling this part fine. But let's also have a lot of part which is called disordered region. And AlphaFold 2 will just correctly put them as this thing we call a spaghetti, just loosely put them in the space. But AlphaFold 3 will have kind of like hallucination like the language model does. It will try to fold them as if they are correct structure. This is not ideal, as this will be affecting with like say protein interaction prediction or like protein ligand interaction prediction. And these are something to work with to think about how to deal with later. And then there's another issue is like we also observe that when we are running inference on large structures, we are seeing the structures sometimes have this problem that they will be like overlapping themselves, or like different chain will overlapping on each other. And this may be related to some issue with the noise in the initial noise in the diffusion noise, or maybe there are some other reason. This is something to keep looking into. Okay, so where's next? I'm going to try to wrap up the talk here. The first thing I want to highlight again of the whole AlphaFold and how it's related to the graph machine learning is, first of all, biomolecules are naturally graphed in the physical space, right? So as we described earlier, this Pairformer thing here, as you can see in the right, they are basically a fully connected graph. And each token here is either an atom, or it can be a group of atoms, which is like a residue in the protein. And what we are trying to do is we are modeling all these interactions. And the way AlphaFold is handling with this is that we are doing this fully connected graph. And this is kind of like probably the best thing we can do at the moment. The reason is like, before you do any folding, you don't know which molecules, which atoms are close to each other. So you cannot quite do a local constraint. So you cannot have a more meaningful, like local physical constraint H. Say, okay, I know this particular atoms is close to this atoms, and these two atoms are very far away, so I don't need to do any H computation. Because before folding, you should not have any prior, say, any two atoms should be close or far away from each other. So the way we handle with this, I would say maybe a little bit brute force, is like, let's just assuming it's fully connected. So every token, every atom can look at each other. And this turned out to just working very fine. But maybe the caveat with this is like, this is also very compute and memory heavy. And as mentioned earlier as well, this means at the training time, we need to crop into a smaller chunk. And if there's maybe a better way to representing in a sparser way, then we can actually training on a bigger crop, or in the training time, we can training on the full structure. And this would certainly be something desirable, because that's reducing the training and evaluation time distributional shift. And also just to mention, protein-protein interaction, which or any other kind of biomolecule interaction, like protein DNA and protein RNA interaction, can also be represented as graph. And it will be very interesting to present this and understand this interaction in the organism. Okay. And there are some future directions that we are pursuing beyond AlphaFold 3. The first one is function prediction. So structure is just an important thing, but it's not the end goal. We actually want to use the structure to help predicting the function. And something very nice as an example is this paper called Alpha Mesons, published by our colleague in Google DeepMind. They use AlphaFold 2 to use this model to predicting what is the single point mutation in the protein sequence that may be causing a functional change of a protein. And at Isomorphic Lab, we actually want to make a full suite of machine learning models to help predicting the function and modulation of the functions. We want to go all the ways from the lower level, the highest resolution, say, starting from quantum chemistry, molecular dynamics. Can we using this kind of simulated data to get synthetic data to train our model to have this like better AlphaFold kind of structural prediction model? And once we have a good model for the structural biology, how can we use that to build predictive interaction, like protein interactome? And can we go from there to predicting the biology? Can we go from there to get a virtual cell? And eventually, can we use that to predicting the toxicity or effect of a drug on a human body or the animal model? Okay, in conclusion, we are very excited about the progress, and we think understanding biomolecular structure is the key. So we want to learn how the molecular machine is working, and we, as shown earlier, we show this is rationally developed modulator to change their behavior. We see understanding the structure is the key for the drug discovery. And AlphaFold 3 is making this not just a dream, it's a dream come true. This actually works. And we can now fold all biomolecules, protein, DNA, RNA, and ligands. This diffusion model works very well. This trained on all the PDB data, and we show this work on novel protein ligand pairs. And we are actively day-to-day using AlphaFold 3 to do regional drug discovery. We use this to predict the novel protein ligand cofold structure, and this speed up our drug discovery pipeline. So we don't need to wait for a crystal structure, which is usually taking at least months to get to verify a structure, but we can just run the model and have a very strong confidence, say we know the ligand is going to, a particular pocket with this particular pose. Okay, so in the end, I would like just to share something about Isomorphic Lab, and we are a very interdisciplinary company. So you can see we have this kind of very different, diverse profile of people, but we are always looking for passionate machine learning researcher and engineer to join our company. And as you can see, we are like having a very happy working environment. And I will stop here, and thank you for your attention.
Thank you for the talk, Alden. There are a few questions the people have posted in the chat. The first one I think might be expecting is more about the sort of choice between equivariance and data augmentation, and kind of what were the main sort of motivating factors between sort of going for data augmentation versus equivariance. Is it something that you kind of tested practically and just found to work better? Was it somehow also sort of engineering motivated? Basically, sort of any thoughts in that? It's
Yeah,
cleaner to kind of yeah. So
sorry
if
you
you have
cut
any
off a little bit, but
no no
I think
no.
go ahead.
No, I was just saying, yeah, basically, if you had any thoughts on that
Right.
in general.
Yeah. I don't know where. Maybe I should just stop at some. Wait. Yeah, I'll just stop at the slide, but it's probably not related to the answer. Yeah. So this is a expected question, as you say, and I mean this is, at first this is just like this is easier to implement. So we started with this, right, and just doing data augmentation, and we actually have some form of investigation and trying to use some kind of equivariance like GNN or equivariance transformer, this kind of thing. And to our experience, it's not working. It works as well, but it's not working better. And I was assuming it's potentially can be more data efficient, but I'll just say in practice, it's working out fine. And the data augmentation just working equally well. And for simplicity, we just go ahead with this simpler design. Yeah.
Okay. The other question is basically on, so one thing you kind of, one thing is that we don't actually have enough data on how the protein evolves through time, typically, so to say, compared to the amount of static structures that we have. There's a question about, are there like good possible ways to also sort of model the temporal evolution of proteins, as I say, conformational changes during docking, for example, get sort of in directions along those. If there are ways to kind of model this well and etc. Yeah.
Can you say the question again?
So the question is basically that one does not actually have easily available data for the actual sort of dynamics and temporal evolution of proteins,
Yeah.
but
Yeah.
are there kind of ways to go about modeling this essentially?
Right. Okay. So yes, so that is a very interesting topic, and I think also a very active topic in the field. That is, it's actually also related to one of the example in the limitation I mentioned earlier, right? So it's not able to modeling the two state correctly. So currently, this is indeed tricky because we are mainly relying on the PDB dataset, which is the crystal of the structure, which is a static snapshot. And this dataset is not a dataset curated for machine learning, right? This is a dataset with like 50 years of hard work from the structure biologists. And they just put whatever important, like they feel they realize and put into the database. So database have some bias. Okay, but so there is the issue with that. I would say one thing is very promising, and I think there are several groups is looking into is how do we combine machine learning approach with molecular dynamics. So can you use molecular dynamic to simulating different state? And with those different state, I think one holy grail, which is very hard problem, is can you really have something like AlphaFold 3 as a generative model, but it's actually generating each different conformation state with the correct Boltzmann distribution. And that is something this would be the next big breakthrough for the protein modeling. Yeah.
I agree. The last question is actually about the transfer learning capabilities when you kind of use multiple modalities. So basically, if you look at protein nucleic acids, these are typically much more data scarce than, say, just single proteins or protein-protein interactions. Did you actually see benefits, for example, if you trained a model from scratch on protein nucleic acids as opposed to doing this co-training between different modalities?
Right. I think this is a very good question. This is actually something we've been recently looking into. I think we don't have very clear evidence, so this is not part in the publication. But I would say there are some good evidence when we co-training both protein, DNA, RNA, and the ligand, we actually get better result from all of the modality. So if we, for example, only training a model particularly just for nucleic acid, it's actually performing like it's performing okay, but worse than a co-trained model like AlphaFold 3. This is kind of interesting because this may not be super kind of straightforward, like intuitive, because they are using different vocabulary, right? But I think it's still like because co-training with this bigger data set of protein is probably getting the model to some better like parameter space that is making it also work for other modality. Yeah.
Thank you. Yeah. I don't see any more questions. Um, but I can still wait on for a couple of minutes just to see if anyone has anything.
Sure.
Yes. So maybe not. But yeah, I would like to thank you for your time and also for the wonderful talk. Um, and yeah,
Thank you so much, and thank you everyone for your attendance.
thank you.
Thank you.
Okay, so we are now moving to the next section, which will be a tutorial session. I think that we can have like a 5 minutes break for people who need to grab a cup of coffee or tea. In the meantime, we will set everything up for the tutorial. Just to make sure that everything is working properly, Peter, can you hear me? And
Yes,
also
yes, I
Olga.
can.
Hello.
Yeah. We are all in the same room, so only I am unmuted right now, but we will alternate during the talk.
That sounds
let's
just
see.
great. Hello.
There's the video.
Can you maybe you wanna try to share the screen to check that everything is working as expected?
Of course. Let's do it. Just a second. How about this?
Yeah, perfect. Great. I think we can still wait 5 more minutes and then we can start.
Sounds good to me.
Okay, so I think we can start. It's 4 p.m. UK time, right on time. It's now time for the last tutorial of the season, titled Neural Algorithmic Reasoning Part 2, From Graphs to Language. This tutorial is a follow-up to the previous tutorial held at LoG 2022, and I'm very excited to see the progresses that the field undergo in this relatively short time span. For this tutorial, we have a big list of brilliant speakers. Petr Velikčović is a staff research scientist at DeepMind and affiliated lecturer at the University of Cambridge. Olga Kozlova is a software engineer at Google DeepMind. Federico Barbero is a third-year PhD student at the University of Oxford under the supervision of Michael Bronstein. Larisa Markiva is a research engineer at Google DeepMind, and Alex Witwiski is also a research engineer in Google DeepMind. And last but not least, Wilfred Bonsi, who is also a research engineer in Google DeepMind. Remember, those sessions are live streamed on both Zoom and YouTube, and the sessions are recorded and will be made available on on YouTube afterwards. Please interact with the speakers using the Q&A tool from Zoom or by dropping questions on our Slack channel. Now, without further ado, let's welcome the speakers. Please, Petr.
All right. Thank you very much, Steve, for the kind introduction. And thank you so much to everybody in the LoG Conference Organizing Committee for giving us the platform to talk to you all about neural algorithmic reasoning for a second time after a 2-year break. A lot of really exciting things have happened, and we cannot be more excited to share all of these great advancements with you all. My name is Petr Velikčović. I'm a senior staff research scientist at Google DeepMind and an affiliate lecturer at the University of Cambridge, and I will be kicking us off for today. We have a lot of exciting things in store for us. So let's dive right in. The first part of the tutorial will be talking about neural algorithmic reasoning on graphs, and it will be given by myself and Olga Kozlova, who will give a tutorial aspect of this work later. Before we dive in, just to note, thank you all so much to all attendees who are joining us along on this journey. And we would just like to call out, this was hopefully communicated to all the LoG attendees, but just saying that this tutorial does have a light prerequisite on the previous tutorial that was given at LoG 22, for which you can find all the materials on our website. And we will actually also upload all of the materials of this tutorial to the same website sometime after it's finished. It's not a must, it's a light prerequisite. It does help a little bit with the understanding. Another thing that we will recommend for a later Colab session is, if you don't already have a Hugging Face token, to please create one. It will allow you to more efficiently go through the tutorial in real time. But once again, don't worry, if you haven't done this, you will be able to follow along and all the materials will be available for you to peruse later. As Steve mentioned, there are many modalities in which you can ask questions to us. But personally, especially because there's so many of us, we're actually all in the same room right now, we will prefer asynchronous questions. So all of us will be monitoring the Slack channel, and whenever we see a question that's appropriate for one of us to answer, we will do that. So we highly encourage you, if you have a question for any of the speakers at any point, just raise it in the Slack channel, the tutorial discussions channel, and one of us will be with you shortly to answer the question. And lastly, but not least, if you enjoyed it or did not enjoy the tutorial and you have any feedback for us, please remember to give it at the end. I believe Michelle will circulate the link in the Slack after the tutorial is over. We would highly appreciate it, and it would mean a lot for us when we prepare future iterations of this tutorial. Okay, so let's get stuck into this. Let's talk a little bit about neural algorithmic reasoning. And specifically, I would like to kind of kick off with a few generic words on all of the key building blocks of the term neural algorithmic reasoning, so that hopefully, even if you haven't come across this term before, you can sort of get a feel for what is it that we are trying to do here. So first, maybe let's dive into algorithms. And already algorithm is something that maybe when I was going to high school, I thought was a super well-defined term, but actually then I went into the textbook on Introduction to Algorithms, which is the authoritative text for this topic, and I saw how an algorithm is defined there. And as you can see, it's not really well-defined even in the authoritative textbook. It's merely mentioned as any well-defined computational procedure that takes some value as input and produces some value as output. There's not really a lot more to go on. In fact, they also mention points like it's thus a sequence of computational steps that transforms the input into the output, and it can be specified in many ways, in English, as a computer program, hardware design, and so on. The only requirement, whatever that is that the specification must provide a precise description of the procedure that you're trying to follow. So this doesn't give us a lot to go on, so maybe it's even better if we ground it in a particular example. And one classical example of an algorithmic problem for which we design algorithms to solve them is the sorting problem. So to be more specific, in the sorting problem, you're given as input a sequence of n numbers, a1, a2 till an. And what you're asked to produce as output is any permutation of these elements. So this will be a1 prime, a2 prime to an prime, which is a permutation of the original elements, such that for some defined inequality less than or equal, these elements are arranged in a sorted order. This is a very fundamental task, which is a building block of many other things we want to do in computer science. And it should come as no surprise, it's been studied a lot by previous literature, and there's conversely many algorithms that solve this problem. One algorithm that you might have heard of, it's one of the first algorithms typically encountered in a undergraduate algorithmics course, is insertion sort. So this is an algorithm that gradually sorts the list by scanning it left to right, and at every step it looks at the current element and inserts it into the partially sorted list up to that position. And this is repeated one step at a time until the list is sorted. This is something you can nicely visualize with a step-by-step trajectory of how the algorithm works. So here we have an input list 52431, and gradually, as insertion sort goes left to right, it readjusts these pointers, the green pointers of the list, such that eventually you will end up with a list 1, 2, 3, 4, 5. And it's a well-defined computational procedure that you can make various proofs that it will necessarily terminate with the final list being sorted. Okay, so that's algorithms, but we talk about algorithmic reasoning. So we need to talk also a little bit about reasoning, and I want to do this in a way that doesn't open a can of worms, because reasoning is such a loaded term in modern artificial intelligence, and if you ask 100 people what reasoning is, you're very likely going to get 100 different answers. So I'm going to make it very clear that this is what we, as in our group at Google DeepMind, what do we mean when we say reasoning? So to us, reasoning is a robust procedure for solving problem instances. And really the keyword is robust. Many of the other things are not so important here. So what this means in practice is I actually don't require this procedure to be fully accurate. I claim that humans are also capable of reasoning. And as you know, humans very often perform only approximate reasoning, especially when you have only partial data available to you, right? And furthermore, maybe this one is a little bit more controversial, but we don't require the reasoning to be provided in a symbolic manner, so in a way that a human can interpret what's going on. We would also be satisfied with a reasoning system that does all of its computations in this high-dimensional latent space without an easy way for us to interpret how it's reaching its decisions. Really, the keyword for us is robustness. It should behave consistently across all instances of the problem that we care about. So if it makes mistakes, it should make mistakes in a predictable manner. And when we talk about predictability across all problem instances, and we're talking about systems trained from data, this implies that what we care about is out of distribution or OOD generalization. This is really the essence of the core problem behind what makes reasoning hard. And this hopefully explains algorithms and reasoning in isolation, the way we see them. But why should we look at algorithmic reasoning as an approach? So to see that, we can talk a little bit about how can we even evaluate out of distribution generalization. And that's something that's quite tricky to evaluate with any specific data set you might have at your disposal today. In fact, you can think about what are the desiderata for a data set that you can use to evaluate such generalization. And really, you need to be able to measure generalization anywhere inside your distribution. So you need to be able to generate outputs reliably, efficiently, for any input you care about. And I argue that these three items together imply by definition that what you need is for there to be some algorithm that produces your data, because the existence of a reliable, efficient outputs generator for a given input is by definition an algorithm, right? And So now we know why algorithmic reasoning. But why do we care about introducing neural networks into the mix? Because algorithms themselves are capable of doing this really well, and in fact, they're very robust. In order to quickly justify this, I'm going to prime you with a question. Find me an optimal path from A to B. I'm giving you no additional context whatsoever, just what would you do if I told you, find me the optimal path from A to B? Now, if you are a theoretical computer scientist, chances are you will see this question and you will react in a very singular manner. You're going to assume that what I'm giving you is a weighted graph on which I'm asking you to find shortest paths from a given source. And you're going to diligently take out your favorite shortest path finding algorithm like Dijkstra and use that algorithm to find all the shortest paths emanating from a particular node of the graph. This is at least how I would intuitively react as someone who studied computer science at undergrad, and I would argue many others would probably react to this question the same. But I have never actually told you that this problem gives you a nice, well-defined weighted graph with a single scalar weight per edge, right? In reality, very often, especially when we care about solving problems in the real world, there exists some real world problem that underlies this. And that might be, for example, a real world vehicle routing problem where you have to deal with not a nice, well-defined weighted graph with a single scalar per edge, but rather you have the status of all the cars in traffic, how fast they're moving. You might have data from the phones in the cars. There might be various roadblocks, traffic lights, weather conditions, all making these estimates much harder. And traditionally, how people would go ahead and solve this heuristically is we would manually try to take this complexity of the natural world and try to map it into something that an algorithm can operate on. Because an algorithm does require the input to be in a very rigid state in order to act in an appropriate manner. But okay, we really cannot hope to always do that manually. So we could also try neural networks. This aligns with the modern paradigm of tool use, where your neural network processes the complex real-world data and produces inputs for an algorithm. But actually, and you can look at the first NAR tutorial for justification behind this, neither of these are likely to be successful for every problem you care about because there's bottlenecks inherently involved in invoking the tool. And basically, it doesn't matter if you have an algorithm that would provably correctly solve your problem if you're executing it on inputs that are incorrectly mapped, right? This is really the problem. Garbage in, garbage out. It doesn't matter what the procedure is. And therefore, this is the justification behind NAR. For higher flexibility, to allow us to be more flexible in this, we can actually try to train neural networks that more closely mimic what algorithms would do, and therefore get the best of both worlds, both a neural network that can process data coming from a more rich input space, and also have it be more robust out of distribution like an algorithm would. And trying to tread this really careful line in a way that satisfies the trade-offs the way we want it to is really the essence of NAR, or neural algorithmic reasoning. Now, okay, so far I'm just talking to you about reasoning in general, but this is a Learning on Graphs conference, and I did promise you the first part of this tutorial would focus on graphs. So why do we care about graphs specifically? Once again, this is an argument that we explore in a lot more detail in the original tutorial, but here's just the one very simple picture that illustrates why graph neural networks are a particularly good representation for dealing with these problems. So on the left-hand side, you see a classical algorithm for finding shortest paths, that is Bellman-Ford. It iteratively updates the distances to each one of our nodes, that's the DU variables, by always computing them as the minimal way to reach a neighbor, so the distance to a neighbor, dv, plus taking the edge from that neighbor to the target node. So that's really what this minimum formula is encoding on the left. And on the right-hand side, you have the computations of a typical graph neural network. And you can see how there's this very nice correspondence between the steps of what the algorithm is doing and the data flow of the GNN. You can imagine the different variables, the DUs, as node features. You can imagine the act of adding the edge weight onto these variables as computing a message function. And you can imagine the act of aggregating across all neighbors as the aggregation function of the GNN. So there's this very nice correspondence between solving different subproblems and aggregating them together that lines up across both GNNs and classical algorithms. And in fact, this is something we can formalize. A landmark paper from iClear 2020 from Keolu Xu and others in Stephanie Agielka's group at MIT has studied this in a lot of detail in the What Can Neural Networks Reason About paper, where they show that, in fact, graph neural networks are a good choice here because they align so well with the paradigm of dynamic programming, which is a very generic paradigm you can use to solve all sorts of classical algorithmic problems. And additionally, this is a concept we explored in subsequent work. In fact, together with Andrew Dudzik, we published this paper on graph neural networks are dynamic programmers at NeurIPS a couple of years back, which explicitly explores a category theoretic setup that aligns graph neural networks and dynamic programming. So hopefully this justifies why should we be doing neural algorithmic reasoning, and also why should we be using graph neural networks to do that. But I've mentioned to you the core idea is this algorithmic alignment. So design parts of your model to align with parts of the thing you're trying to fit. So let's give you a few basic groundwork steps on how to do that. Here is our standard graph neural network equation. So we are updating node features from an input space X to a latent space H. We're doing so by computing a message function psi across every single edge of our graph. We're aggregating all messages using our aggregator function O+. And once we are done with all of the aggregated messages, we combine them into the final node embedding using the update function phi. So what are some different ways in which we can take this neural network expression and make it better aligned to certain algorithms? Well, there's a variety of things we can do. One thing we can modify are the parametric functions, the psis and the phis. One very beautiful example I still love to give on this is from Hung, which was published at NeurIPS 2020 as part of the ITER GNN paper, which notices that many algorithms, such as pathfinding, are homogeneous. And that means they have this very nice property that if you multiply all the inputs by a scalar, lambda, the outputs are actually exactly the same, just scaled up by that same scalar. So shortest paths are a classical example of this. If you multiply all of the edge lengths of your graph by a factor of lambda, you will still have exactly the same shortest paths. It's just that the lengths of the shortest paths will be multiplied by lambda. And this means that if we're fitting a homogeneous task like this, and if we make our neural network components, psi and phi, themselves compute homogeneous functions, we're going to have a much better time. It turns out that to make a standard MLP homogeneous, all you have to do is get rid of the bias vectors, so make them pure linear transformations without the affine part. And that's one of the things that Hung and others do in this paper to great success. So it's just one example of a really simple but beautiful modification you can do to a GNN to make it fit better this particular class of algorithms. We might also want to change the aggregator. And actually, this is something that was my first incursion into the field at iClear 2020. We noticed, so once again, you see the Bellman-Ford example in the lower right corner. All we did really was notice that since the Bellman-Ford algorithm is doing minimization, if we choose an aggregator that aligns with that, like taking the max, that will be much easier to learn the required message functions than if you take a more expressive aggregator like sum. And I'd say nowadays this feels like a very normal decision. Back in 2020, it was definitely contrary to public wisdom. And it was well known, especially around the time when the Jin paper came out, that it was understood that sum was the most expressive aggregator, then average, then max. And max was seen as kind of the least useful of all of them. But it turns out for algorithmic reasoning, that kind of bias is exactly what you need for a lot of problems. And max is now a relatively standard choice in a lot of these problems. But back then, it was a bit of blasphemy. Another thing we can modify are the input features themselves to make the problem more algorithmically easy for the model. One standard example of this are n-body simulations in physics, like the early work on interaction networks from Pete Battaglia and others. And the idea here is when you want to fit n-body systems and their trajectories, often the forces you need to model between them follow an inverse square law. Gravitation, electrostatic forces, they all decay with the square of the distance. So if you put just raw distances as your edge features, you might not have such a good time because your message function, the function computing the force, now has to compute an inverse square rule. And this is quite tricky. But if instead we feed the inverse square of the distance as the features, now suddenly the required message function is linear in your features, and it's much easier to extrapolate. So even something as simple as being mindful of your feature engineering can make a big difference. And lastly, you can modify the computation graph, so the neighborhood of nodes over which you compute your embeddings. And one standard example of this is the pointer graph network that we published at NeurIPS 2020, where we explicitly force the edges of our model. We rewire our graph to align with a with a pointer-based data structure like disjoint set union, and this gives us a much better theoretical time complexity requirement. So these are all the various things we can do to a model. But let's say you've now proposed a really interesting thing, update to a model, and you want to test it out or write a paper about it. How would you go about doing it? Back in the day, it was really tricky. Every paper had to design its own data set. It was a bit like the Wild West in there. It was really hard to compare results across different publications, which prompted us to propose what is now known as the CLRS benchmark. And really, it's just a collection of these classical algorithmic skills we might want our model to respect in various ways. So as the name implies, CLRS 30, it's a collection of 30 benchmarks tasks from the CLRS textbook, Introduction to Algorithms. And even though it's only 30 algorithms, it already spans a wide variety of skills: sorting, searching, pathfinding, string matching, and even geometric algorithms. And this is a publicly available benchmark that we published at ICML a couple years back. You can access it, play with it, use it for any data set you might want for any publication. We've already had a lot of very happy users over the years. We hope that whatever that something we say today will resonate with you and lead to you also using this benchmark. So what does CLRS offer to you? It actually offers a unified graph representation for a variety of algorithms. Here you see Bellman-Ford that we discussed before, as well as matrix chain multiplication, a classical dynamic programming algorithm. And you see how the library gives you access to the entire step-by-step trajectory of what this algorithm is doing as it's gradually computing shortest paths or optimal ways to multiply matrices. Or also sequential algorithms are represented as graphs. So the already mentioned insertion sort is represented, as well as a string matching algorithm like the naive string matcher, which tries to find the first occurrence of one string in another. So all of these algorithms are specified using a fixed number of probes, and those just track the various variables that the algorithm is using during its execution. And those variables may be used either as input, or the model might be queried to predict them as output, or they might be used both for input and output. So the model might be asked to track their state over the lifetime of the algorithm. And once you specify these probes, this uniquely determines what the data set is going to look like, what the encoder and decoder architecture should look like, and what the loss function should be. So CLRS 30 is not really just a single data set. It's a data set generator and a baseline generator, because you can specify any new algorithmic task. And once you use the CLRS language to specify the probes of that task, the library will take care of everything for you. So it will design the machine learning model, design the batching, design the loss functions, and Olga will show you a lot of this later on in the tutorial. Like, you basically don't have to do almost any machine learning if you set things up the way you want to. And I want to briefly walk you through the representation of CLRS 30, because as I said, we have this common graph representation. So specifically, we're going to be looking at insertion sort again, and I'll mention to you the 6 probes that are being recorded in the insertion sort specification. The first such probe is the position probe. We have this as a nice tiebreaker for all of our different algorithms and a way to nicely encode positional information. So a position probe is just something that's given as input in each node of the graph, and it's a scalar. It's just a scalar encoding what is the index of each one of my 5 items in this case. Then we also have the keys. Note I'm highlighting at the bottom trajectory what these different probes are in the picture. So keys are the actual input node scalars telling you what are the values to sort. So the 5, 2, 4, 3, 1, those will be encoded inside the key probe. Then what we want to predict as the output is the final state of the sorted array, these green pointers at the end telling you what is the predecessor of each node in the sorted list. So this is now at the output stage. For each node, we're predicting a pointer to the previous node. Yeah. Now, of course, we can track how these pointers evolve over the lifetime of the entire data structure. And this gives us this pred h, which is also a node pointer, but it's a hint type, meaning we track it over the lifetime of the algorithm for every node in the list, what its predecessor is over time as more and more items get sorted. And this is all exposed to the model, so it can use it as input, predict it as output, whatever is most preferable. And lastly, we have 2 additional node masks, which tell you of certain elements that the algorithm is currently focusing on. The first one, the blue pointer here, I, is telling you for the currently considered item where in the partially sorted list it will land. And also you have another sweeping pointer, which just goes left to right over the list, telling you what's the current element being sorted into place. So all of these are exposed in the setup for the model. And as already implied here, all of the probes can be either inputs, outputs, or hints, or live on nodes, graphs, or edges. And they can also be of different types like scalar, pointer, and mask. And inputs and outputs are fixed during execution, whereas hints are something where you have whole trajectories of them during the lifetime of the algorithm, and they actually specify the algorithm. Note that all sorting algorithms, as long as there are no duplicates, will have exactly the same inputs and outputs. The only place where they differ is how the intermediate states will change. Now, as part of these slides, we have this nice animation showing you how these representations travel through the model and how they get embedded into nodes, how they get embedded into edge features, and how all the mask features also get encoded, and how the GNN then processes them. I'm skipping quickly through this because this exact same animation exists in the original NAR tutorial. I'm just leaving it here. It's going to be in the slides that I already shared. It's going to be here for your convenience, so you can easily see all of these things that CLRS does automatically for you. All of the data passing you see here, you don't have to implement it yourself. Once you've specified the probes of an algorithm, the CLRS benchmark takes care of all of this for you. All of these losses, data passings, encoders, decoders, and so on are all done for you. Now, of course, because we already mapped everything to the same graph representation, why should we stop at learning just one algorithm? Why not have one graph neural network that can learn all 30 of them? And this is exactly what we tried to do in some prior work. So what you imagine here is you have this unified graph processor network, and you have for each one of your tasks, like sorting, pathfinding, or finding the convex hull of a set of points, you have for each one of them a separate encoder function, fi, and a separate decoder function, gi. Those map to and from this latent space, and they're generally really simple. And the question was, can you train a single architecture like this? It turns out you can. We developed an upgraded model called triplet GMPNN, which we used as a foundation of our generalist neural algorithmic learner that we published actually at the inaugural LoG 2 years ago. And here you can see the performances of the multitask single architecture in orange across the 30 algorithms out of distribution versus the baseline single task expert in blue. And you can see there's some differences. Sometimes the multitask model is much better. Sometimes it's much worse. But on average, the performance of the two are quite comparable. And therefore, it led us to believe that we can indeed train just one model that can fit all 30 of these algorithms at the level of a single task expert. So this is roughly everything that led us to 2022 when the original NAR tutorial was given. So what did we miss? What happened in all this time since 2022 that is worth paying attention to? So slowly and steadily, starting from triplet GMPNNs, which augmented the normal GNN equation with message passing over explicit triplets and gating mechanisms, and also sinkhorn decoders for tasks requiring permutation outputs. And this already achieved a really solid performance across the 30 algorithms, as you can see on the left. Since 2022, this research just kept growing. The first such instance published at ICLR 2023 were relational transformers from MSR, which show what you need to change inside the transformer architecture to make them a bit more competitive on these tasks. Specifically, most transformers don't have an easy mechanism to incorporate the edge features, which are really important for graph tasks on NAR. So what you do is you just let the edge features constitute part of the query and key vectors and value vectors, and this suddenly allows you to have a more competitive transformer architecture. Additionally, G4GetNets, published at this year's ICLR, they actually leverage the idea that these algorithms are designed to be Markovian, and therefore they have an explicit gate mechanism which actually allows the model to explicitly forget some proportion of the previous embeddings of their processor network. And this led to a lot of really outstanding results. As you can see in the table, a lot of the algorithms are now at out-of-distribution performance above 90% accuracy. And most recently, we've done something blasphemic, which is published this year at LoG, the RENAR model, the recurrent neural algorithmic reasoner, where we actually set the aggregation function to an LSTM, therefore dropping all notion of permutation equivariance that is very beautiful and important for graph tasks. Well, we argue that in CLRS, this might actually be not such a bad thing to do, because for a lot of these algorithms, like list algorithms and so on, we have an explicit canonical node order that we can feed into our LSTM. And actually, we get not only really good results at certain list algorithms, but actually we get a double digits 80+% performance on quick select, which my good friend Michael Galkin called out in a recent blog post that is very unlikely that it's going to happen this year. Well, it turns out all we had to do was drop permutation symmetry, and we had a model that's capable of solving quick select. And actually, when you take all of these results together across the state-of-the-art models, there's only 3 algorithms left where we don't have above 80% score on the original out-of-distribution test set used by CLRS. That's Floyd-Warshall, Knuth-Morris-Pratt, and strongly connected components. Hint, hint, these are directions you might be interested to focus on in the immediate term to help us completely crush the existing test set. And then in the future, we're going to have an even bigger distribution shift because this one is just too small for a lot of these specialized GNN executors. Beyond these main architectural advances, we've also done work to endow graph neural networks with memory mechanisms. And 2 works that I think are worth calling out here are the recursive algorithmic reasoning module from Jonas Jurs, Dulan Jayalath, and myself that was published at LoG last year that endows GNNs with a stack, and neural priority queues that I published with Rishabh Jain and Pietro Leo at an ICML workshop last year that endows GNNs with a priority queue style data structure. So these both endow GNNs with a persistent memory component, which can be leveraged for more precise and more robust answers, even across bigger distribution shifts. Another thing that's quite important is I've mentioned how critical these trajectories were and the hints to the system performance. In fact, there's been several papers arguing that if you just naively learn to predict the next hint given the previous one, it might not be so good. So Sadegh Magdavi had this great TMLR paper where they basically showed that for many classic CLRS algorithms, not using the hints was sometimes a good idea. This prompted several other works, like this paper from Gleb Rodionov and Lyudmila Prokorenkova, that you can actually have very handy crafted supervised losses that let go of hints in their entirety, but still allow you to execute out of distribution with great accuracy. This was published at NeurIPS last year. And also recently, because many algorithms really require you to find the fixed point of a certain operation, Dobrik Georgiev, J.J. Wilson, and Davide Buffelli have shown in the forthcoming NeurIPS paper that will be presented next week that you can use deep equilibrium models to greatly stabilize the training dynamics of these models. Now, of course, this might paint a slightly daunting picture for these intermediate states. So should we just get rid of them altogether? I would actually argue we had some papers recently that say that hints can take you a long way if you use them properly. So if you don't just do simple next hint prediction. So one approach that we used last year was to show that actually the trajectories of algorithms will often have exactly the same initial few steps if you transform the input in some predictable ways. So here for depth first search, we have this trajectory exploration from node 1 to node 2 to node 3. Node 3 has no neighbors. We go back to node 2 and explore node 4. That next step, exploring node 4, will still be exactly the same even if we attach all of these different nodes and edges to the graph. And we might want to exploit that to design a more fine-crafted contrastive objective. And specifically, the hint relic method, which Beatrice Bevilacqua and us published at ICML last year in Hawaii, was to basically use this to design a contrastive learning objective where we contrast a step in the original hint trajectory with against incorrect step in an augmented graph. And this gives us a very rich space of contrastive learning to use. And actually using this, we set one of the current state-of-the-art results. Another recent very exciting result that will be presented at NeurIPS next week, the open book NAR method, actually not only uses the hints from the original method, from the actual input that you're trying to predict the output for, but also we give the access to the model of the entire training set of all of our sequences. That's why it's called open book. So typically when you as a human tries to execute an algorithm, very often you will look at examples of previous executions to ground your predictions better. And it turns out if you give your model explicit access to the training set of possible reference sequences, this can give you a much better NAR performance. Once again, a more non-trivial way in which these hints can be used. And I mentioned previously we can align all these different parts, parametric functions, aggregations, features, computation graph. You might wonder, is there anything else left to do? Turns out there is, and it wasn't even in this plot. There was this implicit clock which says that you always have features at time t, and they all work together to compute features at time t+1, and this is perfectly synchronized. But this might not be an assumption we might always want to hold, because many algorithms we might want to fit are asynchronous, meaning that we can only update a handful of variables at each computation step. Yet all of our models, GNNs, transformers, and otherwise, are fully synchronous. They update all of our nodes everywhere all the time. And if you think about it, what kinds of out-of-distribution generalization can you get from message and update functions in such a model? Because they have to learn an identity function almost everywhere, and then like highly complex functions somewhere else. And it's quite tricky. So better alignment with asynchronous algorithms might be a very useful future direction. And we had this paper with Valery Engelmeyer and Dobry Georgiev at last year's LoG showing that this might just mean let's try to execute as parallel as possible algorithms, and that's just better for GNNs to do. That's easy to prove, elegant, scalable, but obviously not all algorithms are embarrassingly parallel, so we can't do this. So there have been a variety of methods like Guac and cooperative GNNs that used explicitly asynchronous message passing, where at every step you only pass some of the messages and you only receive some of the messages. This obviously directly solves our problem inside the architecture, but it's quite tricky to scale on modern hardware, which typically requires things to be done in parallel. And there's many discrete decisions to make when deciding which messages to send and which messages to receive. So actually, we worked on asynchronous algorithmic alignment with Andrew Dudzik, Tamara von Glen, and Razvan Pashkanu, where actually we tried to tread the middle ground. So we designed GNNs that are still synchronous, so efficient to execute on a GPU or a TPU, but make them provably invariant under various asynchronous execution traces. This leads to a pretty cool monoid equivariance style result, and it hits a sweet spot between a method that is theoretically sound, scalable on modern hardware, and also feasible to implement. So I highly ask you to check it out if you're interested. It was published at last year's LoG as a spotlight. Lastly, what about different applications of NAR or more theoretical understanding? How has that developed in the last 2 years? In terms of places where NAR has been deployed, the 4 areas I'd like to call out are we used NARs to get better predictions in neuroscience, predicting blood vessel types in the mouse brain. This was the dual algorithmic reasoning paper with Danilo Numeroso and Davide Bacciu that we published at ICLR 2023. Then they've broken into computational biology with NARs. Dobry Georgiev and others have published the NARTI paper, which uses these NARs for trajectory inference over gene expression data. They are also seeing usage in harder combinatorial optimization problems. The CONAR paper from Dobry Georgiev and Danilo Numeroso was published at last year's LoG, shows how you can pre-train a model on polynomial time algorithms and then use that model as a great foundation for MP hard problems and get better performance at fitting them. Lastly, together with Yefimia Panagiotaki and several other collaborators at Oxford, we worked on using these NARs to get better performance for an algorithm that's critical for point cloud registration in robotics by basically automating the steps of that algorithm better. What about theory? Well, we believe that fitting algorithmic invariance requires to step beyond geometric deep learning and model things that are not just purely equivariant functions. This prompted us to develop the categorical deep learning framework at ICML, together with Bruno Gavranovic, Paul Lessard, Andrew Dudzik, Tamara von Glen, and João Araújo. We have published this at ICML earlier this year at Vienna. Then the great work from Artur Bagdeluca and Kimon Fontolakis at Waterloo has shown how you can use looped transformers to exactly simulate many NAR procedures that you might care about. Of course, this still doesn't tell us exactly how to find such loop transformer parameters, but it's a great encouraging step that such classes of architectures are in the right direction. Then 2 really exciting works on quantifying out-of-distribution generalization better. This work from Andreas Lukas, Martin Kus, and others that was released on the archive earlier this year. There's a great step towards quantifying out-of-distribution, and also a great step from Bruno Ribeiro, Uriel Leskovets, and co-authors on the Graph Metro paper that improves the out-of-distribution generalization through a rigorous and motif-based approach. Lastly, I'd like to call out 2 recent quality of life improvements to CLRS that Olga will tell you all about in her tutorial to follow. The first one is, in the basic CLRS benchmark, we always use fully connected graphs, and the Salsa CLRS work from Minder and others in Roger Wattenhofer's group at ETH that was published at LoG last year actually shows that if you use sparse graphs in the algorithms where that is possible, you can generalize to much bigger structures than what CLRS will allow you in and of itself. This is a repository that's a public PyTorch-based fork of CLRS that you can find on GitHub. And lastly, but not least, through the work of Vladimir Mirjanic and others that was published at LoG last year, we actually now have a nice way to visualize what these algorithmic executors are doing over time and plot their trajectories in PCA space, sometimes discovering really cool patterns over how these models process data. Once again, all the code for generating these beautiful plots is publicly available on GitHub, and we'll also tell you all about it in the forthcoming tutorial. That was it, and I hope you enjoyed the first part of the talk of the tutorial for NAR over graphs. I'm now going to hand over to Olga Kozlova, who will tell you all about a Colab tutorial that covers a lot of these concepts. Thank you so much, and Olga, the stage is yours.
All right. Hello, everyone. Give me a second to share my screen, and we can start. So, hello everyone. My name is Olga, and I'm a software engineer at Google DeepMind. And basically, in this tutorial, we will walk through the code snippets of how you can train and evolve your model on CLRS-30 benchmark. We will look into novel architectures and multi-algorithm training, and we will also explore the libraries that Peter just mentioned. To make the experiment kind of clear, I will restart the session, and we will walk through this Colab. It starts from the lib installations, which I conveniently installed while Peter was giving you a talk, so we don't need to actually run them. Then we import the libraries that we need and initialize the JAX random number generator. Here we have two helper functions. One prints the data sample, and another draws the plots for train losses and validation accuracy. We don't need to get into them, but they are helpful to us. Now let's recap briefly how you generated the data based on the tutorial 2 years ago. You would create a sampler for each algorithm, specifying the number of nodes in each sample, and you will iterate through it. And it will look something like this. You will see the spec, which basically shows you all the variables used in algorithm, and the data batch will look somewhat like this, containing the lengths, the hints, the inputs, the outputs. What we can do now is we can use these create samplers functions. And as we see in documentation, we can use it to create samplers for training, validation, and testing, setting out the train lengths, the val lengths, test lengths, and the algorithms that we want to use. Same as I do here. The parameters I choose don't really have specific reasoning for that. Apart from that, I choose the validation length in distribution and test length out of distribution. And this is just the two algorithms I like for the shortest path. So yeah, let's print data batches from the new samplers. And we see that we have two batches, one for each algorithm. And the spec list is also changed. Now we have two of them. Now we need to create a model. And we do this exactly as we did it before, with small change. We have added new models. For example, the triplet GMPNN model that Peter mentioned, kind of really great one. It is that you can use it as easily as you did it before. Let's see how we can load it and use it. So yeah, here we specify the parameters of the model. Then we pass it to CLRS baseline model, and then we initialize it. This is the kind of JAX feature that in order to start using the model, you need to unit it first using the example batch of data. Here, I will just save the checkpoint for just initialize the model, and I will use it in the second part. So this is the train loop. I will start the training first and then walk you through the function. Basically, what we do, first we initialize some lists for losses and accuracies. Then we do the for loop for like 500 steps. And each loop, we first do the training step, where we go through all the samplers for all the algorithms, do like the feedback step, and collect the losses. Sometimes we will evaluate the model once every 50 steps. In this case, we will also go through every validation sample and evaluate the model, basically. And sometimes, if the current accuracy is much higher than the best so far, we will run the evaluation on the test set as well and save it, and save the model if it's the best one. So yeah, here's the training. Goes not that fast, not that slow, so we will need to wait a minute. And then we will draw the plots to visualize what's going on in terms of loss and accuracy. A few more steps. Yep, great. So we see the loss decreasing for both algorithms. So this is the Bellman-Ford, and Dijkstra, and accuracy for both of them as well. Now let's look into the library, which allows you to visualize the trajectories of each sample. So the narrow latent spaces library. We will need to do a few more imports. So what we do here is we choose an algorithm on which we will see what happens. And I will create kind of a test data set for that. Another thing that I actually forgot to mention when I initialized the model, let me get back to it, is that here we add debug equals true parameter. This is a new feature which was just added, but it allows you, apart from the current predictions and hence, it allows you also to return embeddings from each time step. So we will use them to visualize. And yeah, if it's set to false, which is by default, the model will behave as it did before. So yeah, with the fact that we know that the model is set to debug, we expect this third output of models predict to be this stacked. I will actually walk through it in a second. Basically, what happens in this function is we first initialize some arrays for the trajectories and for the lengths. Then we go through all the samples in which we have like, yeah, approximately 16,000. We dump these trajectories. Then we gather them all together in one list. Then we concatenate them along the batch axis. And then we need to move on. Very, very confusing. Let's look at it step by step. So the cartridge shape is time steps, batch, nodes, and feature. What this means is that for each time step, we have a batch of samples, each containing 12 nodes, I think. Yep, 14 nodes and features, like 128 features. So we gather these all together. Then we collect them for all samples, getting all trudge. And what we do then is we reduce the nodes axis because it's quite tricky to track embeddings across many nodes. So yeah, we want to have just one point for them. We do it. We use the element-wise max because this is basically the same aggregator which is used in Celeris processors. So what we do next, and the transpose is basically just to change some dimensions afterwards. So it will be easier to use by the library. So the two experiments we will do here is that we will build some plots for the trained model and for just initialized and see what we have. All right, we have all the data for both of them. Now let's visualize. Briefly going through this function while the plotting. So these lines are just like purely technical. We create some folders for the plots and then set up some experiment setting, like plotting setting. Here we have 16,000 samples. Obviously, they will have different trace lengths. So we need to select only those who have like equal length of the trace. In this case, we want to choose the most frequent one and filter only these lengths. So we choose the most frequent one, and then we filter the data and the lengths using it. And then we pass it all to the plotting functions from the library. And here's what we have. So for just initialized model, so these two plots, what we see here is that we aggregate the graph embedding for each step and project it in 2D or 3D space using PCA. And we draw a line between different steps. So we choose like 50 samples, and we draw 50 lines for different for one sample for different timestamps to see how it changed through time. And for untrained model, we see that nothing really useful happens. The samples diverge. There is no clear solution here. But on the other side, this is a small spoiler, but like on the other side for the trained model, we see that these samples actually converge in one place. So they start from the blue and converge to the red. And we also can see that the distance between the initial point and where the samples move is quite big in the beginning, and then it becomes smaller and smaller. And the second plot we have is, instead of having one PCA model for all the points, we do different PCA models for every timestamp and add the timestamp axis, having this 3D representation. So as we see for untrained model, the points are quite spread, while for the trained model, they all kind of, well, still not super in one spot, but like we trained the model only for 500 steps. That's very little, but we already see the difference. And this is just like a few plotting functions from the library. We encourage you to go and explore what's available there, and also check the paper. It has much better description of what's going on. And the last part that we will walk through is the sparse training. We need to restart the kernel here, and I will explain why. So we need to import again everything we need, but the good thing is that we need only imports and the part 3, so we can hide the part 1 and part 2. So yeah, we will explore Salsa serverless library here. The good thing is that the execution will be faster, but it has only 4 algorithms available from the CLRS 30 and 2 additional ones which you can check in the paper. And another significant difference is that it uses PyTorch. So yeah, this is just for you to know, not advantage or disadvantage, just a different thing. And the experiment we will set up here is that we will run the small evaluation on like 10 samples for the CLRS model and for Salsa CLRS model and datasets, and check the VRAM usage. And the reason why we needed to restart is because there is no easy way to reset the JAG. JAG's memory kind of starts. And yeah, so we just restart runtime and run from here. I will launch the code first and then explain what's going on, because it takes about 3 to 5 minutes to actually run it. So we initialize the model, this we've seen before. And then we have a for loop where we create data samples from like 2 to 4,000 and run a short evaluation loop. So it's really short one, the num samples just done. I will do it for BFS algorithm and choose BGN model for both CLRS and Salsa CLRS. We measure the RAM usage this way. So in JAGs, we measure peak bytes in use and divide it for this number to get megabytes from bytes. Yeah, here we will need to wait for about 3 more minutes, because the bigger the size, the longer we need to wait. And I expect that we even might hit the runtime error because we take too much memory. As you can see, it already grows significantly with every step. While we wait, I will describe the Salsa CLRS function as well. So in these lines, we just remove the standard logging because we don't need it in this experiment. So the output will be as nice as this. Then we initialize the model, loading it from the config, and yeah, build the dataset to init the model. Then we do same loop. We can reset the torch settings here, build a dataset, go through it, measure the usage, and save it. And we still have some time to wait until we evaluate the last bit. Yeah, and afterwards, what we will do, we will plot the RAM usage for both of them together and see how significant the difference is. In this sample, usually it takes quite long, but hopefully right now it will be quite fast, because the most significant part is dataset generation. But because I already have run this Colab while Peter gave you the talk, they should be cached. So do you expect that if you launch it first time, it will be much longer than when I do it? And another note I forgot to say right in the beginning, that we are using the TPU. First of all, because we're limited on time here, and we want you to actually see what's going on. And secondly, because here, for example, the example in the salsa Celeste library for RAM usage, they used the decoder device. So yeah, this is super fast here. And let's plot. So basically, this is re-implementation of the plot from the paper. The blue line is the CLRS line. The orange one is salsa CLRS result for both for PGN models. And this is the side of graph. The blue line stops here because later it hits the out-of-memory error. But despite that, you can see that the difference is very significant. And we can see that using salsa CLRS is a much more efficient way. But it had, like, obviously, it's up to you what to use. But we wanted to highlight that there are some advantages and disadvantages of different libraries. And I think with this, I will stop. This is all that I wanted to tell you. I am happy to answer the questions in the Slack channel, so please post them. And right now, I will hand over to Federico. But he will be using same laptop, so we will just switch places.
Hello. So let me just share my screen. Here, yeah. Okay, hopefully everyone can see it, or else you should probably tell me now. So yeah, I'm Federico. I'm a third-year PhD student in the University of Oxford. And yeah, I'm happy to be presenting the part on language models. So I appreciate that a lot of people are coming from like graph neural networks perspective. So maybe not everyone is like super familiar with language models. So I'll give a very brief intro to them. So most language models actually use transformers, at least most of them like deployed. And so they're autoregressive, and we'll kind of look into why this is important. And the way they work is they essentially take text and they split it into tokens. And the tokens are kind of like really the basic unit that this language model uses. And the process of turning text into tokens is done by something called a tokenizer. And this tokenizer is kind of independent from the training of the language model, but they are quite sophisticated. And they're actually very important for the performance of the language model. And then these tokens are really just like IDs that the tokenizer gives to text to split it. And then the part of the language model is kind of taking these token IDs and turning them into like token embeddings that then the transformer can process meaningfully. And the language model is really a function taking token embeddings, or really it's a function from text to text, of course, but there's some kind of intermediate process in which you turn text to these tokens. Tokens are processed into final embeddings, and then these final embeddings are somehow processed to tokens or to text again. And this autoregressive process means that really the language model is predicting at one step, it's predicting a probability distribution over what it thinks the next token should be. And then it's doing this repeatedly. So you really only generate one token at a time. And maybe we can kind of illustrate a bit more tediously what this means. So here we have this input, which is like, what is 2 + 2? And this tokenization is the one that I believe would be the one that like ChatGPT would be doing. So it's splitting like words, and usually like digits are treated independently. So numbers will have their own token usually, or maybe multiple tokens. And then you feed this to the language model, and then you extract the next token, which would be the in this case. And then in what you do is then you refeed this this into the language model. So you've generated a new token, and then you refeed this new sequence where you added this additional token to get another token. And then you do this again, and you get another token, and so on. And so from this, you go like, what is 2 + 2? Then the model can generate like the answer is 4. So here, even like spaces can have their own tokens. Like tokenization is actually very complicated, and it's not like it's kind of like this dark art that makes language models work. And these transformers usually usually are called decoder only transformers. And so this decoder part essentially means that they're using what's called a causal mask. And I think people in GNNs will be quite familiar with masking. This is how you kind of encode the topology of the graph. Well, the causal mask really just means that like we have this lower triangular mask. And this is important because essentially it's saying that tokens can only attend to tokens coming before them. And this is quite useful because at least as a training trick, of course, because now you can, if you didn't do this, then it would be kind of hard to train models because the attention would be like looking ahead. So if you're trying to predict the next token, then you could easily like overfit to this and like not generalize at all. And importantly, these transformers are actually extremely deep. So like the 400 billion parameter llama model has more than 120 layers. So these actually are extremely deep transformers, and it's kind of remarkable that we can build such deep models and they work so well. So just in equations, again, this is all like relatively simple, of course, but like so we compute first raw activations, and these are based on the queries and keys. So here I'm kind of showing the computation based on like you fix a token and then you look at all the keys. And then these activations are simply the dot product between the two. Then people can modify this a bit, but let's say here you're not using positional encodings. And then what you do is you apply a softmax, and this softmax is simply kind of the standard way of taking a vector in Rn and turning it into a probability mass function over n things essentially. And then what you do is you do a linear combination of this. So you take their values and then you linearly combine them based on the attention. And importantly, this sum kind of goes like only looks behind you, right? So like this is the fact. This is coming from the causal mask. Okay, so now we can start talking about reasoning. I want to give in this talk maybe more of an overview because I want to kind of introduce people to a lot of different concepts, which I think are actually very related to what people are working on in graph neural networks. One of the kind of very pivotal papers, which is also quite recent but extremely popular now, is this idea of chain of thought. And this comes from the observation, like from pretty nice observation. It's like this fact that if you give a model, like these examples are from a data set called GSM8K, which is a data set of like kind of simple math questions, but usually like word problems and so on. If you give a model like this prompt, you can see that it gets the answer wrong. But instead, what you can do is like you can kind of make it try to explain what it's doing. So the difference between left and right is that here you give it in the left, you give it an example in which you just ask it to spit out the answer. The answer is 11. While on the right, you kind of tell it how it can potentially reach the answer. And in this sense, like the model is trying to explain itself, right, when it's answering the question, and somehow this helps with performance. Now, there's also like people use this kind of different terminology. So there's like a difference between scratchpad and like k-shot prompting. So k-shot prompting is like, in this sense, in this example, you'd have like k is 1. So before the model is answering this question about the cafeteria, you give it an example about tennis. So this is like why you give it one example. If you give it 2, it'd be like 2-shot prompting and so on. And then there's also this idea of scratchpad. So in some sense, scratchpad is like allowing the model to use additional tokens to do computation. So for example, in some sense, in this output, the model is doing some kind of scratchpad computation where it's not just telling you the answer, it's also like kind of saying how it's arriving to the answer. So usually these two are used at the same time, but there's like a slight difference between the two. And actually, I think this can relate to a lot of work that people do in graph neural networks, which is that of like looking at the expressive power, connecting it to the Weisfeier-Lehmann test, and so on. People have done similar things in analyzing the expressivity of chain of thought. So kind of analyzing how, like, does allowing the model to kind of compute intermediate tokens actually help theoretically? And the answer is yes. And perhaps this is not super surprising if you kind of look at transformers from the point of view of like automata and so on. Like, you can really view these kind or like Turing machines. You can view these kind of chain of thought process as allowing the model to have extra tape or extra memory or so on. So in this plot from this recent iClear paper, what they kind of show is like that you can in one way increase the amount of chain of thought the model is able to do, so that it can capture a broader class of algorithms. In fact, it can fit like even polynomial time algorithms. And then instead, you can also give it more embedding size, and this is kind of like giving it more memory. So these two are kind of two directions chain of thought can help. Of course, embedding size, it's probably like, it's kind of constant, but chain of thought, you can give it maybe more, you have more freedom in this. But this is kind of a way in which people have theoretically shown that chain of thought actually has some theoretical benefits. Of course, these analyses usually have some restrictions. So they'll assume like hard attention, so attention only attends to a single value, or sometimes they do like this kind of softer hard attention in which you can have multiple values, but it's all uniform. So you need to make some simplifications, but this is a nice computational model. And I don't want to maybe go too much deeper into this, but I'm linking here some papers. Like, so for example, there's this whole like kind of line of work about complexity theory, which is kind of what I was talking about now. But there's also like very interesting work regarding this, like this introduction of this new kind of programming language, which is called RASP. And RASP is essentially a programming language that mimics the operations that a transformer can do. And the people have, for example, observed that if the kind of task you want to solve has a small equivalent RASP program, then the transformer will be able to generalize better, or at least fit this task better. So it's kind of nice that people are going this direction of like trying to formally understand transformers, but also these kind of connections to programming languages, or what kind of programming languages they can implement. For example, this tracer work is kind of showing how to implement, given a RASP program, how to get an equivalent transformer out of this. So I think these kind of works are quite interesting, and I'm assuming will be interesting to people who work on GNN expressivity. Okay, so now let's talk a bit about length generalization. So I guess, as Petar mentioned, we're really interested in building, well, I guess now also language models capable of performing robust computation. And really, for us, we can try to restrict ourselves, at least for the scope of this talk, to length generalization. And this is the ability to extrapolate from short problem instances to longer ones. So, I mean, probably it's clear why you'd want to do this. So you want your model to generalize, but there's also some more subtle like advantages to this. Like in general, you can like shorter sequence data will be more abundant. It's easier to get data that's shorter, and also it's computation more efficient to train on shorter data. So it's not just a nice thing to have, but there are also some kind of practical considerations that making a model that's good at this kind of helpful. And so to this end, there's this benchmark that Larissa and others in the group have worked on, which is this CLR's text benchmark, which I guess Larissa will talk a bit about more in the Colab part. But essentially, CLR's text is a direct translation of the graph benchmark into text. So in this case, there's like this insertion sort example where you can tell it the initial state, and then you can give it the trace of the algorithm and ask it to predict the final step, or you can ask it to predict the entire trace and the final step. So in some sense, this is like taking the graph CLRS benchmark and literally translating it to something that an LLM can like symbolically try to manipulate. And this is quite nice because a lot of benchmarks in language models like GSM-8K are kind of word problems, and they're harder to maybe generalize in terms of making them longer or more difficult or have more inputs. While in this kind of benchmark, it's absolutely trivial. If you want to make it more difficult, you can just give it a longer array to try to sort. So this is why this kind of procedural generation is very useful when you're trying to benchmark models and you want to do this robustly and kind of check generalization this way. So here there's an interesting plot from the paper, and what they show is, so first of all, this green line is this Gemini 1.5 Flash, and where it's attempting to solve the CLRS text benchmark. And you can see the performance is essentially 0. This model is huge compared to this 2 billion parameter Gemma model, which was instead specifically tuned for this task. And you can see that the Gemma model, even though it's much smaller, has been tuned on it, and it's much, much better at the task. And these red dots are kind of the in distribution dots, while everything else is out of distribution. So by in distribution, I mean that the model has been trained on these sizes, while where you don't have red dots, it has not seen these sizes. So on the right, when you in kind of 35 to 40, this is the extrapolation regime, while the other one is like interpolation. So you can see that, Gemma seems to be much better. And also there's like this kind of plus RPE, which stands for some type of position encoding improvement, which also helps the generalization. I'll talk a bit more about that later. But here you can see for many kind of data sets, this is one model being trained to solve all of them simultaneously. And you can see that, tuning, of course, helps, but you can also usually see, for example, in naive string matcher, a lot of them, like in extrapolation, so in length generalization, the models really drop in performance quite quickly. So I spoke a bit about position encodings. Now, position encodings really impact length generalization. And for example, the ones that they showed in the plots are these randomized position encodings, and at the end I have references to everything, so you can find everything I'm talking about. But then there's like a lot of people in general have also looked at position encodings and tried to develop position encodings that generalize better. And the main intuition is that for length generalization, you really care about how these position encodings behave in the limit, or at least like as kind of your sequence gets larger and larger. So FIRE and RPE are nice examples of this kind of careful type of study. Then people also developed embeddings specifically for certain operations. So for example, these abacus embeddings, which are designed specifically for arithmetic type of operations. However, most LLMs still use these rope positional embeddings, which are probably like the most common at the moment. And rope were motivated because essentially they decay the activations as the distance between tokens increases. And this is the plot which they showed, in which you can see this kind of decay as the relative distance increases. But instead, actually in our very recent work, we showed that this does not really have to happen. And this only happens when these queries and keys are the same vector. And so we have some kind of more like kind of mathematical analysis on this. And so, for example, what we actually show in our work is that like rope actually helps in probably length generalization for different reasons. So, for example, it allows these models to build very specific attention heads. So, for example, here you can see these like head 5 and 8 are very distinct from the other patterns, and this is kind of what we show in our paper. We really kind of dive deep into like what's happening into these kind of embeddings. Now, I won't go too much deeper into detail, but there's a reference here if you want to check it out. But my main point here is that like length generalization, well, position encodings play a huge role in this, and actually understanding them is extremely valuable, and because they're still quite poorly understood. And now I want to talk a bit about information propagation in these transformer models. And I want to show a motivating example, which is this counting task. So here we ask Gemini 1.5, like, can you sum 1 + 1 + 1, etc.? And this kind of x-axis is how big this 1 + 1 sequence is, and the y-axis is the absolute error. So how far off is Gemini? How far off is the answer? And you can see that already at this task, Gemini is really bad at doing this. And in fact, for many kind of related problems, it's quite bad. So here, for example, is like counting just the ones in a sequence of ones. And similarly, we kind of try with chain of thought, with few shot learning, trying to make it like use chain like a scratch pad. It doesn't really work. And these are huge models. I mean, Gemini 1.5 was at the time like the kind of the best Gemini model we could find. And this kind of like, there's a question here is like, is this like a very fundamental issue, or is this like just we need more training, or for some reason they're not trained on summing 1 + 1 + 1, etc. So to check this, maybe let me show you a nice experiment. For example, let's say we prompt Gemini, how many ones are in the following sequence, and I give it k ones. And then how many ones are in the following sequence, I give it k + 1 ones. So 1 and 2 only differ that 2 has an extra 1 at the end. And I plot the norm difference between the last token at the end of the transformer. So this, I'm using Gemma 7 billion parameter model Gemma. And you can see that as the k factor kind of grows, the representation gets closer and closer. And this is an issue because at some point, you can see there's this BF16 precision. At some point, if the sequence is too long, the two sequences will have the same output representation. So they're forced to make a mistake. So essentially, the two representations become indistinguishable as k grows. It falls under the floating point precision. And this is what we call representational collapse, which is in some sense analogous to oversmoothing. There's some slight differences, but it's some kind of result about oversmoothing. And we make this more formal. There's like a few assumptions you need to make, but yeah. So we pretty much verify that this occurs in Gemma 7b, and this points to this kind of issue in transformers that like just due to this effect, like counting in these kind of styles of prompts is forced to break at some point. And there's also a similar effect, which is due to the causal mask. So this causal mask is, again, like this lower triangular type of mask. And what happens is that information still has to reach this like Y5. So at each layer, at some point, you need to extract this Y5, which is like the representation at the last layer of the last token, because then this is like what you then softmax to get out the next token. So the softmax only looks at this last token. And the basic intuition here is that, like, let's say your token V5 and you want your representation to survive into Y5, there's only one path for your representation to kind of survive, and it's if these attention coefficients are quite large from V5 into V5. Instead, if you're like at V1, there's like many paths that your representation can take, and kind of allow it to survive. So for example, in this diagram, the blue starts to dominate simply because it essentially has more paths that reach Y5 compared to the red. So you can see nicely in this kind of illustration here. And like a corollary is this, like we have some experience in the papers like that copying the last token for language model is harder than the first. And this is because essentially the information from the last token is much harder for it to survive into the representation of Y5. We have many more details in the paper, but I guess one of the takeaways is that like phenomena like over squashing and over smoothing are actually also present in language models, and in many ways they're kind of analogous. And I think this connection between language models and graph neural networks, or at least transformers and graph neural networks, has been kind of known. But what's very interesting to me is that like these phenomenon, you can kind of start studying them from the point of view of like text, and like how do these phenomena relate to like tokenization and text and all these things is very interesting. And then the fact that they then imply some kind of failure case into in some problem is I think maybe something that people in graph neural networks are quite interested as like an application of these like over squashing and over smoothing results. Okay, and now I would like to talk finally about the softmax function. And the softmax function is really one of these like key functions in machine learning, and they take a vector and turn it into a probability mass function. And it has nice properties, of course, relating to like entropy and so on. And it has been shown actually many works in previous years. So some works at NeurIPS and this works at Colab that some tasks like may suffer from this dispersion of the softmax. And by dispersion, I mean as you add more tokens, the softmax is forced to lower attention to the existing tokens. And this is simply because everything has to sum up to 1. And now if you add more tokens, like it's like tokens cannot have 0 probability, because the only way for them to be assigned 0 probability is if their activation is negative infinity. So of course activations are all bounded, so this cannot really happen. So for example, in this plot, what we show is like for this max retrieval task, as you keep doubling the sequence length, at the start your max retrieval is correctly attending to the correct token, but as soon as you go in length generalization, so out of distribution, the softmax has to disperse more and more until it's essentially uniform. And this kind of points at the fact that like the softmax function makes it quite challenging for you to be robust to very sharp types of operations. And a nice way to formalize this is perhaps through entropy. And entropy is really just measuring like how close to uniform your distribution is. So the highest entropy distribution is exactly the uniform distribution. Now, this kind of Shannon entropy is defined on discrete distributions, because in continuous distributions, it's actually not as well behaved. But we're softmaxing discrete distributions essentially, so we're fine. And here, what we plot is we give Gemma some inputs, and we grow the underlying sequence size. So the sequence is like similar to the ones we had in our transformers need glasses papers. So like, can you count the number of ones? And then you give it a growing sequence of ones. And you can see in these plots that the entropy in the attention heads grows as the number of items is increasing. And this is kind of showing how like this distribution is becoming more and more uniform, simply as a function of the number of items which are being given to the model. And in some sense, this can be used to argue that like things like copying or very sharp very sharp operations cannot be robust unless you have like things going to infinity or negative infinity, right? So then you can have the softmax can build delta functions, but of course we cannot do this. In fact, what we show in the paper is that what really bounds you is like the spectral norm of the Aquarian key weight matrices. So these are the ones that kind of tell you how sharp your softmax can be, because softmax being translation invariant, really all you care about is the kind of range that the softmax values can have. And this range is precisely given by the spectral norms of these weight matrices, because these are the ones that define the range in dot product. So for example, what we show is that like changing the temperature or things like this can be used to artificially sharpen the softmax. And if you're interested in this kind of work and like the relationship between softmax and entropy and out of distribution generalization, I invite you to check out our preprint, which it's this paper here. Okay, so just as a summary, we studied decoder-only transformers, and we saw, for example, techniques like chain of thought, and we kind of described how these can provide additional expressive power, like not only in practice, like empirically, but also theoretically. And we really focus on length generalization, which is this problem of like you have a problem or you have a task you want to solve, which the number of inputs can grow, and you want to generalize. You want to be able to solve it regardless of the number of inputs. And we saw how like CLRS text is a nice way to kind of benchmark this. It's like a natural kind of paradigm to test length generalization. We also saw how position encodings play a big role in length generalization, and this is, I think, a very interesting and active area of research. And then things like the Capsule mask and how this relates to oversquashing due to the topology or representational collapse, so some kind of over-smoothing idea. And then we also saw how there's like issues in the softmax. The softmax is dispersive. So this points to like some issues in generalization just from like the architectural level. So of course it's very interesting now to like take these findings and like try to improve and on our current models. And this is kind of what we've been trying to do in our work. We try to point out issues and then try to somehow fix them due to now that we have a better understanding. I have left also a bunch of references. Of course, this is not exhaustive, but hopefully it's a good way to get started. Some on chain of thought, on expressivity, on RASP, on length generalization, position encodings, and other like miscellaneous ones, which you might find interesting. A lot of them we did talk about in the slides, but not all of them. So maybe hopefully these slides act as like a nice resource for people trying to get into this kind of research. And now I'll hand over to Larissa for the Colab. So I'll stop sharing. Yeah, and thanks so much.
I think we can't hear. Larissa, sorry, can you hear me? Oh. Larissa, sorry to interrupt you. Trying to reach out to arrow. Yeah, Larissa, can you hear me? Because we can't hear you.
Let's try one more time. Can you hear me?
Okay, no, yeah, no, yes. Perfect.
don't hear
Yeah,
well.
sorry, I tried to contact you and I didn't manage to.
So, is it okay now?
Yeah, I can hear you loud and well.
Okay, great. Sorry for this. What about screen sharing? Does it work now?
Yeah, we can see.
So we can, okay, let's start over again. Sorry about this.
Yeah, apologize.
I apologize for this. Okay, sorry, attempt number 2. Hello again, my name is Larissa. I'm a research engineer at DeepMind, and today I'm going to show you a Colab, which should kind of gear you up with everything you need to conduct your own experiments with CLRS and large language models. To start, at the beginning, I want to emphasize that I use a Colab Pro version to prevent any preemptions, because actually fine-tuning of a large language model is a compute demanding thing. So that's why I use Colab Pro to prevent any preemptions, but you can try to use a free version. It's not a problem, but sometimes you might get preempted. So, and wait till the Colab schedule gives you another batch of compute. So for this Colab, I use a G4 GPU kernel of the Colab. You can find it there. So if you click connect, if you try to change runtime, so my setting is T4 GPU, and this is high RAM version because like usually you need a lot of memory in your experiments, and it's better have more than less. So at the first step, we just install all packages, Python packages we need, and after them being installed, we are good to go for setting up the environment. And as the first step, we are going to set up Hugging Face token. So here's the instruction how to do this. You need to do to the Hugging Face website, set up the token, and then put it there into a special form to save a key which allows you to access a Hugging Face repository. So the thing is, why do we use Hugging Face? Hugging Face, it's actually an industrial level standard right now for large language models. This is the most popular library. It contains a lot of different models, a lot of different pre-trained weights, and it's very easy to work with it. So that's why we chose it. And as soon as you have your secret key and token, your secret installed, and Hugging Face token is loaded into Colab secrets, you can use it. You just need to import a correspondent library and then just ask the library to give you a token. After this, we need to do some minor environment setup. It isn't very tricky. I just switch off this pre-allocate thing in JAX to make more memory on GPU available, because JAX usually tend to pre-allocate quite a lot of memory for itself, for its own operations, and there we don't really need this. So I just switch it off through this through setting up this value. And create a random number generator keys for further use. Let me run this for you. Yeah, and in the final, before I carry on to loading the model, I just want to make sure that everything is set up right and we are really having deal with GPUs. And because that's very important, it's very hard to fine-tune model, for example, on CPU. But as you can see, I checked our default backend, and this is GPU. This means we are good to go. So to the loading and creation of the model using Hugging Face is pretty straightforward. For this, you need to choose the model name from the Hugging Face repo index. In our case, this is a Google Gemma 2B model. Then I set up some quantization parameters. This is just a technical part. Quantization parameters for our model, and then I load the tokenizer. Tokenizer, this is, you can think about it as a program which translates text into numbers and vice versa for the model, and then to do the backward transform after the prediction. So as you can see there, I tell I use the Hugging Face token to access actually tokenizer because it's loaded from the Hugging Face repository. And after having the tokenizer, I load the model. Also, as you can see, I pass the model ID, which is the name from the repository index. I pass the quantization parameters, name the device, and finally provide the access token for the function to be capable to load the weights. This model has only 2 billion parameters, but in fact, it takes around 5 gigabytes of memory. So yeah, it's quite big, and it usually takes, as you can see, a few minutes to load everything into your Colab. But as soon as everything loaded, we can experiment with it. So while it's loading, I can just show you the test inference. So as soon as model is loaded, you can ask it about something to just verify whether everything is fine with model, whether like our setup in terms of accelerators, GPUs, etc., works well, or we have some problems. And just for this purpose, you can just ask the model something. In this case, I asked the model, what would you be if you would be whatever you want to be? And funnily enough, it started to advertise me some Netflix series, which is pretty funny. Now, good news, we actually have our model loaded, and we can conduct our experiments. But before we try to teach model something, we need data. So in the following section, we are going to actually create our own version of CLRS text dataset. and then apply it as a source of data for fine-tuning process. So initially, in the talk, you might notice that CLRS has a variety of algorithms implemented, so it can generate samples for different tasks, to ask model to solve different tasks. There are 30 different algorithms we can employ for this in CLRS. Some of them are pretty trivial. For example, you have just searching of minimum in the array, but some of them are pretty advanced. For example, we have optimal BST. Yeah, yeah, there are many different things and different types. Also, you have some sorting algorithms, string-related algorithms, many of them. Dijkstra as a graph algorithm. So, but let's imagine we choose something and want to generate our first data set. To do so, I provided you a function which does this. It's defined there. I'm not going to go into the depth about the code because it's quite self-explanatory. If you'd like to, you can just read through it and use it. That's why I jump just to the main call, which creates the data set. So in this example, we want to create actually a very simple data set, which comprises two algorithms, Bellman, Ford, and BFS, and it was in the previous tutorial, and use two lengths for each of this algorithm of size 8 and 16. For each unique combination of algorithm names and task length, we are going to generate around 100. We are going to generate 100 samples. Yeah, and then when all samples are generated, we are going to split the initial big data set into two sub data sets, where trained data set takes 80% of the initial of all samples. Validation and test data sets take 10%. So when everything is generated, you'll receive the dataset dict object, which this is a very typical data type for Hugging Face and PyTorch. And this dataset dict actually contains train, test, and validation datasets and provide all necessary interfaces which you need to run Hugging Face fine-tuning function. So this is kind of a nice wrapper which frees you from any hassle with data as soon as you have it. And now let's look into actually the content of this data set. And there I print actually one sample, the first sample from the trained dataset. And we can see there that there are kind of two records inside of the sample. The first record is marked with the user role, and the second with the assistant role. The user, actually the text is about setting up the task. What are we going to ask the model? And assistant record is about the answer we expect to have. I'll explain why data is formatted in this way a little bit later. So, and actually, the main idea is since we have rows, this is a special way to signal the model which part of the text is expected to be like the user input and which part of the text is expected to be actually the model output, the model answer to the text. So, but obviously, usually large language models, they take only like plain text. That's why we need a special function which turns this into a proper text. For this purpose, I imply the technique which is called chat templating. You can read more about it via this link. But generally speaking, what it does, it takes your initial sample and actually turns it into a plain text plus some special tags which like add some additional information, per se, signals to a large language models. For example, there we have this, again, this Bellman-Ford example. But after applying tokenizer with this chat template to this data, we have a very nice plain text with special symbols. For example, BOS means beginning of the sequence. So this one marks the beginning, actually, of the sample. Then we have start of the turn and end of the turn. These two tags actually separate different rows from each other and let model to understand where is the data input from the user and where is actually something which we suppose the model has already predicted, and we are trying to maybe continue through autoregressive prediction. So yeah, and as we can see, we now have our text formatted. And the only thing left I need to do before we start our fine-tuning process, I need to define a function which will automatically convert this original sample into the tokenized version, which I just showed to you. So for this purpose, I defined this function. It's very simple. I just take the input sample and convert it. And let's see how this works. I indeed took the first sample of the trained data set. And, you know, to be fair with the model, I don't want to show it the answer. That's why I removed the agent answer from the sample and convert it into the text and get a really nice and plain text function, plain text with tags. And then I feed it into our model. And as you can see, things don't go well because the model has never seen this format before and has never, most possibly, tried ever solved problem like this. That's why it makes an attempt to answer something to our question, but utterly fails. And that is to say, we might want to have a model which is like, you know, specialized, that is to say, fine-tuned on our data to conduct our further experiments. So for this purpose, we are going to run a fine-tuning process using LoRa. LoRa is a low-rank adaptation techniques which allows you fine-tune large language model like kind of cheap, because like if you try to fine-tune the entire model, it has that many weights that most possibly it won't fit into accelerator, and it might take a really long time to train like a big model from the scratch. That's why people came up with like, you know, simple and cheaper solution of doing so. What do they do? First, we say that we are not going to train the entire model. We are going to train only the subset of layers. And for each layer, what we do, we take a layer and actually freeze it. We don't change it during the training, but what we do in parallel to this layer, we create two layers, two smaller layers. I mean, one side of this layer is usually of size D, but the internal side is kind of a set of two bottleneck layers is R, and R is usually very extremely small. So that's why you have this low rank thing into the name of low rank adapter. And you have two sequential layers of low rank. And actually, in fact, you train them instead of frozen weights. And as soon as you pass data through your frozen layer and through the set of layers during fine-tuning step, you just sum them up together, and this is your new representation, which passes by further to the next layer. When the fine-tuning process is over, what you do, you just multiply A by B, and you have a new matrix of size D by D as the original weight matrix of the layers was, and just add them to the original frozen layer, and you actually per se have a new weights for your layer, which you just replace in the original checkpoint, and this is it. You fine-tuned your model. You fine-tuned your layer. So, and actually, when you have your model loaded, when you have your data prepared, it's pretty simple to kick off the process. You actually define LoRa config, where you say how small the rank of your low rank adaptator is, what kind of layers you are going to train, and what kind of layers you are going to train. For more details, I encourage you actually to go to this to this tutorial, which describes in depth all possible detail and tricks you might use to fine-tune the model. Yeah, and as soon as your LoRa config and the rest of the things are assembled together, you can just kick off the SFT trainer function and train your model. And it takes approximately maybe 10 minutes, or even less, 4 minutes, to see the results. So there we did very little steps. We actually did 200 steps. But we can see that the last function went down. And that is to say that, model inhibited some changes in its behavior. Otherwise, our last function won't change. And yeah, and we want to actually see what's the difference now between what we used to have, so this pretty strange answer there, and what we have now. And so for this purpose, let's feed one more sample into our model. And as we can see there, now model maybe, so we've done a very few steps there. Model, maybe the answer might not be right, but now model is doing its best to follow the structure we provided even after a very few steps, like 200 steps for the model. It's very little. But due to some reasons, I don't know why, but the model decided to identify itself as Diego instead of the model as we used to have there. Let me show you this place. Where is it? Yeah, there. But overall, there is definitely a positive tendency in its response. So if you fine-tune model for longer, you will definitely have much, much better results. And in the final, I just want to show you a few tools which might be useful for your research. For example, you might see beautiful pictures from the Federica paper. So many of them were obtained by the Penzai library, which allows you to visualize the internals of the model. So you might see the weights, for example, of heads, the activation, etc., etc. And this actually helps you a lot to understand what's going on inside and why model respond to your question in one way and another. So this library works not only with Google models, but with all models which are presented in Hugging Face repository. So if you'd like to do some nice visualizations for your research, definitely give it a shot. And in the rest of, this is just a very short code, the code that allows you to load models and to save your model after fine-tuning, load it back, and again, feed data into it, for example, to continue your research and your investigation about different things related to reasoning and maybe something else. So actually, this is it I wanted to show you. I hope you enjoyed our presentation. And now I think I hand over to Alex and Wilfred, right? Mm-hmm. So, yeah.
Sorry, do you hear me well?
Yes, thank you.
Okay. Hello, and thank you for attending tutorial. This part I would like to talk about neurosymbolic reasoning as well as NAR, neural algorithmic reasoning, specifically on language and graphs. In this third and final part of tutorial, we will tie both parts together and define how GNNs can alleviate several of the issues of the decoder-only transformer. My name is Alex, and I'm a research engineer at Google DeepMind. So I would like to start with motivation. So we all experience different kind of basically avalanche of large language model coming to the to every corner of the society, but surprisingly, they're very unstable and fragile when it comes to out of distribution reasoning. So like one of the recent papers, like a GSM symbolic, this very simple modification on of GSM data set, like basically varying like just names and values, you'll see huge drop on performance for all modern large language models. So like, even worse than this, like just adding irrelevant information to problems, performance drops up to like 65%. And not only this, so this is like just a slight shift of distribution. But if you would consider maybe like a harder reasoning problem, like for example chess, or like puzzles, we will see that with scale of the problem, which bigger and bigger we have number of combinations, like performance of such models drops rapidly. So like, and I think there's certain similarities with how people perceive reality and how they think. Like just small just example, like on the first board, like if it's like an average probably club player, we will spot immediately that he or she can fork queen. But on the second board, when we need to have 3 moves to basically do the same, it's already harder and requires something. So it's deliberate thinking and like planning and reasoning. So like it's certainly true that like with more and more data, I mean with bigger and bigger training, like becoming a master or grandmaster, you can start recognizing this position. The same true with LLMs. With a huge amount of data, you definitely like raise the bar, and you can kind of automatically detect and solve certain problems. But this does not imply that you solve reasoning, because like you still can face bigger problems, or still you can go out of distribution. So I would claim that like if any size of LLMs, there will be always problems that are unsolvable in like in single pass. So like we always will need to find like certain solution to like reasoning. It definitely there are many ways of doing this, but the problem is there. We want. I think our goal is try to solve problems which are not in training set. So basically going out of distribution. Like, and another small example, like I think this was released recently, is Zebra Logic, benchmarking logical reasoning ability of language models, which like measure different performance of different language models on grid puzzles. So grid puzzles is a simple puzzle with like bunch of logical statement, and you need to find, for example, matching. So like who lives in what house, or who owns certain things. And like testing on human, we already see that like with larger dimensionality for the puzzles, time required for human to solve it grows dramatically. And so we would expect as well, like for LLMs, need more resources or better algorithms to solve this problem, or probably both. So like and we can take inspiration from like fundamental work of Daniel Kahneman about thinking fast and slow, like who defined like concept of system 1 and system 2. System 1 being fast, automatic, and quick system, so which operates effortlessly with no sense of voluntary control. So this application is human. And system 2 is like requires attention and like effort and basically logical step-by-step reasoning. So it's frequently associated with agency or concentration. So I think combining those, like assuming that like LLMs solved significant part of like fundamental like pattern matching, I think the reasoning still has way to go. So I would just add 2 quotes of Leslie Valant, who made fundamental contribution to learning theory. So he claims that most fundamental aspects of intelligent cognitive behavior is ability to learn from experience and ability to reason from what we learned. Other quote from Yosha Benjo, it's maybe old quote, but it still I think holds true, that current machine learning systems are weak when they're required to go and generalize beyond training distribution. So like just to briefly look on this system 1 and system 2 characteristics, we can see that they're very much complementary. So like if system 1 is fast, maybe in the sense implicit, but system 2 is so slow in the sense that it requires multi-step logical algorithmic reasoning. So the same is like we may think that system 1 is can easily utilize parallel processing. System 2 usually does have some sequential element in it. So the same is fixed compute, like if system 1 is maybe fixed compute, or system 2 is definitely require variable amount of compute with bigger and bigger problem sizes you need to solve. I think like even with analogy with human, like maybe average human reaction time is like 200 milliseconds, but you cannot definitely solve complex problem or chess puzzles in 200 milliseconds. And you definitely need to also apply some deliberate logical step-by-step reasoning. So the same goes about the distribution, out of distribution, and pattern matching and such. So like I think it's very nice and kind of a nice idea to combine those systems together, and definitely was done before in many different ways. I would argue that like AlphaZero system, like which combines some Monte Carlo research and like deep learning network is one of the approaches. There's also like narrow Turing machines which emulate algorithms, or AlphaCode. Maybe we can think that like system 1 construct system 2. So there are definitely many different approaches, but many of them are very fruitful and promising. And today we want to look in one of those, like we work from our group, like it's TransNar, and Wilfred is going to present in detail this work. So yeah, please take the driver's seat.
Alex, can everyone hear me? Well,
yes, we can hear you.
Okay. So hi everyone, I'm Wilfred, a research engineer in the Foundational Research Unit at Google DeepMind, and today I'm going to. Can everyone hear me?
Yeah, we can hear you, but we don't see anything.
Yes, just weird. Okay, just a second. Okay, I can't see my slides. I'm not sure why. Alex, are you still controlling of this?
Sorry, we don't hear you.
Can you hear me?
Yeah, we can hear you. We just see your face, not your slides.
My slides, okay. Okay, let me just share the slides then. So I'm not too used with Zoom, so it's a bit. I thought Alex would be presenting.
There should be like a green button, which like share screen in the bottom of the interface.
Just a second. So can you see the?
Yeah, great. We can see it.
Okay, so if I
this. Can you see my? Okay, perfect. Sorry, I'm really not used to Zoom. Okay, so as I was saying, hi everyone, I'm Wilfred, a research engineer in the foundational research unit at Google DeepMind, and today I'm going to talk to you about our work on augmenting large language models with neural algorithmic reasoners. And so the motivation behind combining LLMs and NARs is pretty straightforward. LLMs, as you all know, are really good at communicating in natural language, but they still struggle with robust algorithmic reasoning. And on the other hand, NARs have been shown to be quite good at this kind of robust reasoning on symbolic graphical inputs. So the big question that we tried to answer was, can we get the best of both worlds? Namely, can we get a model that can robustly solve algorithmic problems specified in text? And to answer this question, we proposed a hybrid model whose architecture is depicted here. You can see it involves transformer layers with an R, and it simply implements a unidirectional cross-attention mechanism between the NAR nodes and edges and the transformer's tokens, essentially. So the transformer updates, so the cross-attention updates the transformer's tokens representations using the computations performed by the neural algorithmic reasoner. And the dataset that we used for this study, or the two datasets that we used, are the CRS30 and the CRS text dataset, which I'm assuming you should be familiar with by now, since they were covered in earlier tutorials. But if not, we have a reminder of what a sample from this dataset looks like. Here you can see that the green part, so you can see a sample here for the insertion sort algorithm. The green part corresponds to the input, the trace is in blue, and then the target against which we evaluate the model is in red. So for this study, we didn't really use traces at all. So we were trying to predict the target, so the output given the input directly. So we built the TransNar from a transformer model of 70 million parameters equipped with ROP plus randomized positional encoding. I think Federico mentioned how this randomized positional encoding can help with our distribution generalization. And in this study, we wanted to, have the transformer as powerful as possible in terms of, so that we wanted the baseline to be as good as possible on our distribution of generalization in general. So we equipped both models with randomized positional encoding. We trained both models, so the TransNar and the transformer, on 7 epochs of the training data, which included training sizes of 4, 8, and 12. We then evaluated both models on auto distribution sizes 10, which tested the interpolation capabilities of the models, and 14, which tested extrapolation capabilities. We considered both the cases where the base model was pre-trained and the cases where it was not pre-trained, so randomly initialized. And this in practice corresponds to whether you are in a fine-tuning regime or in a pre-training regime, so in an initial training regime. Our results showed that the TransNar significantly outperformed the baseline, so the pure transformer, on most categories of algorithm, as you can see here, in both the extrapolation and the interpolation regime, and this was consistent across whether you pre-train the base transformer or not, essentially. So at this point, we've established that we can indeed build a hybrid model that is good at solving algorithmic problems specified in text, right? But the obvious issue is that it requires 2 input streams at inference time, text and graph, when for a lot of problems of interest, you only have 1 at inference time, so usually text, right? So the question is, can we do better? Can we get rid of the second input stream? Can we get rid of the requirement of having this accompanying graph representation of the problem? And to this end, we explored distillation. So we tried to see if we could distillate a TransNar model into a pure transformer model in such a way that the transformer recovers the or somewhat recovers the improved auto distribution capabilities of the TransNar. So here are some of the experimental details for the distillation. As I just mentioned, the TransNar was the the model that we the teacher was the TransNar model that we had just trained, so the one trained on sizes 4, 8, and 12. The overall student loss was computed as a convex linear combination of the ground truth next token prediction loss, restricted to in-distribution problem sizes only, and the teacher distillation loss, so the percent entropy between the teacher log hits and the student's prediction. And these were weighted with the convex linear with a factor in a convex linear way. So the student training sizes included 4, 8, and 12, for which both the ground truth and the teacher supervision were provided. And we also provided teacher supervision for sizes 10 and 14, just so the teacher can somehow teach or show the student how to behave in this out of distribution setting. But because we provided signal at these sizes, we call them soft. We kind of call this regime soft OOD. So the student test sizes included 6 and 10, which tested the interpolation capability, and 14 and 16, which tested the extrapolation capability. And furthermore, 10 and 14, because they were kind of seen through the teacher's log hits, we refer to them as I mentioned above, soft outdoor distribution sizes. So we evaluate on these soft outdoor distribution sizes, but we also evaluated on the truly never seen by the student sizes, which are 6 and 16. So these were never seen either by the by the student, neither via the ground truth loss, neither via the teacher supervision. So these one are kind of true outdoor distribution sizes. So this is it for the experiment details of the distillation experiments. And yeah, so we so here are the results, and again we show them for various outdoor distribution regimes, including the the interpolation regime, which here corresponds to 6 and 10, and the extrapolation regime, which corresponds to 14 and 16. And we already mentioned that 10 and 14 are kind of this soft OOZ sizes, because we provided teacher supervision for this lens. But we also have 6 and 16, for which we never provided any kind of signal or supervision signal to the learner. So these are more like the true outdoor distribution test, if you will. And you can see that. So what we're looking at here is the comparative of the performance of the different models according to, depending on the value of alpha, and alpha was simply the coefficient of the distillation, of the teacher supervision, essentially in the distillation loss, in the final distillation loss. So an alpha of 0 means that there's no teacher supervision, and it also means that it is our baseline. So we're training a pure transformer model on the in-distribution cross entropy loss. So that's our baseline. And any value of alpha that's greater than 0 is a distilled model, because it kind of benefits from the teacher supervision. And the baseline here corresponds to the red bar then. And you can see that across the board pretty much, and for the various algorithms considered, the red bar is always most of the time at least is the one that's the smallest, which means that the distilled transformers from the transformers distilled from the TransNar are most of the time better than the regular transformer. So yeah, so at this point we've shown that we can build this TransNar hybrid architecture that performs better than the transformer, but we've also shown that we can then use it to train a pure transformer model that's also better than some transformer that you just train on the in-distribution sizes of your data. Okay, so let's now look at the limitations of the approach. So the first one that needs to be highlighted here is the dependence on initial graph representations. So even though with distillation we kind of we're able to circumvent that at inference time, we still nonetheless need graph inputs to even train the TransNar right before distilling it into a pure transformer. So yeah, we still depend on having, you know, one-to-one graph inputs that are one-to-one in like that map one-to-one with the, you know, the text inputs, and that's not always the case. So that's one limitation of the study. The second limitation regards the distillation experiment that we ran, and you could see in the results that it's not always clear which distillation factor to use. Yeah, it kind of looks like it depends on the task, and it wasn't particularly clear to us how to determine that automatically. So yeah, so the natural order limitation is we need to, like, you know, maybe investigate that more, like how to find the optimal alpha for, you know, a given scenario, and also maybe consider you know, using ensemble decoding techniques where you, for example, would train multiple distilled models with, you know, with different alphas, and then maybe decode from this ensemble of distilled models using ensemble techniques used in usually used in the field, such as, you know, majority voting, or even doing something more on the weights of the different models. In your ensemble, you can, for example, do weight averaging, and then, you know, decode from a model that that derives from this weight averaging, right? So how exactly to you know, how exactly to choose the distillation factor, and more generally how to deploy the distilled transformer models is still unclear. Okay, so moving on to the conclusions and next steps, just as a reminder, we have introduced the TransNar model, which is a hybrid architecture combining the language understanding of a transformer with the robustness of reasoning of a pre-trained GNN-based neural algorithmic reasoner. We have shown through an evaluation on CRS text that this TransNar is much better than a transformer in terms of our distribution generalization. We've also shown that we can distill this TransNar into a transformer-only model, which is also better than just a transformer trained on, you know, on in distribution data. And we hope that, you know, future work will investigate expansions of interest, notably in, you know, in mathematics, logical inference, and common sense reasoning. And that's it.
Thank you. So now I will show small demo code integrating TransNar and Gemma model. So give me a second, I will try to share the screen. Okay, so in this scope, we will just try to have small demo how we can combine Gemma model and TransNar GNN-based architecture. So it's based on the work of Larissa. So a lot of things we are going to do is the same. So we need to install a bunch of packages, to bunch of dependencies. We do need to use Hugging Face token. This for basically like a Gemma model is open weights model, and it's hosted on Hugging Face. So to access and download model, we need HF token. Like you can configure it here, and if you have Hugging Face, you can get value at settings tokens. Okay, I think we are done with installing packages. Then like just setting up environment. It's the same way. So like most of experiments in the paper were done on 70 million model here, but the Gemma obviously bigger. Just few parameters you can. This is a 2 billion model, 2 billion parameters, meaning like non-embedding parameters. It has 18 layers, 8 heads, and like 256 head size. So we okay, maybe let me double check if it's loaded already. Yeah, so we can after loading the model, we can inspect contents of the model and structure. So as you see, it's composes of 18 JAMA decoder layers, which each layer is attention layer followed by MLP layer with rotary embedding and normalization. So you can briefly expand explore configuration as well, like just model config. So after origin model, we can do small tests that like verify that model does work as expanded. Oh, let me probably still word it. Yes, that may take a little bit of time, but yeah, it's okay. So we in meantime we can export model and model parameters. So this is 4-bit quantized model. So this is pre-trained. Okay, let me check status. Okay, origin checkpoint. Yeah, I think it should be fine. So let me double check inference. Yeah, okay, so inference does work. So we use generate method and basically point prompt, we can get something out. So now we want to quickly integrate TransNar. So it's the slightly difference. It's because we are using pre-trained model. We just use monkey patches or change JAMA forward, JAMA model forward method. So we can supply TransNar hiddens. So in the original paper, how it's done, we basically have like a frozen pre-trained Ghanem processor, which provides information to the tokens in the transformer. But here we simplify stuff, so we just use NAR hiddens like storage as with input data. But what we will do, we will create basically like in TransNar, we add like cross attention after each layer in transformer. So like let me just do this like so we can PyTorch we can just insert a bunch of these layers like so we get like double size of layers, and we can verify that model is changed. Okay, so after okay check. So yeah, we have like casual LLM model, which after every second layer is NAR cross attention layer, which gets provides information to the transformer. So like in cross attention, we queries are coming from tokens, and keys and values are coming from Ghanem. Okay, so yeah, we can maybe do a few checks. Yeah, so this is like input IDs. This is what tokens are transferred to. So like after the tokenization is done, like every token gets an ID. So like in this JAMA model, it's I think 256,000 tokens is used. Each of them then like go through embedding, and then like we provide it as an input to the model. So here we can we have right now they're on Google Drive, but probably we'll move to other source like this TransNar activations, so you can load them together with data. Basically, like this is CRS data, like which consists of query answer algorithm. So give a second, we can probably load, you can load this train and validation data sets, verify content. And like using this data, we can basically like run our model, and with appropriate loop, we can also train it. Okay, just a few checks. Okay, so yeah, we can get data. This is like formatting is the same as basically what is used in your work. So like we can utilize this formatting, And yeah, we can go through further paths and like add maybe small training loop here. Yeah, I think it's basically what everything which I wanted to show. So it's I think its TransNar idea is very promising, and like we, as Wilfred described it, there's a lot of extensions which we can build on it.
All right, so that was the last part of the last session of our tutorial. We have finished with about 30 minutes to spare. We've tried to be quite active in answering questions live in the Slack, but if there are any other things you would like us to address while the whole team is in the virtual room, so to speak, please let us know. We'd be very happy to talk more about this. As you've seen throughout these 2.5 hours, we are generally very passionate about reasoning. So this is a topic we love to talk about at length. And we hope you enjoyed it. Please do leave some feedback at the end. That would really help us prepare future editions even better.
Yeah, absolutely. Thank you very much. And thank you also for being so in time. While we leave some time to the audience for typing some question, maybe I can go with like a very broad and general question, which will be, which are in your opinion the next steps for NAR? So where do you see it from here to the next years, the next steps, let's say?
Okay, that's a great question. It feels like something that all of us should try to answer. So maybe I will start, and then we can go in the order in which we gave our answers. So Olga, Federico, Larissa, Alex, Wilfred. So in my opinion, well, what I'm personally most excited about the future of like these NAR methods and their applications, I feel like with LLMs, as we described in Federico's part and also through the TransNar that Alex and Wilfred talked to you about, we've sort of started to describe how a tiny GNN, which in reality is much smaller than what a big language model might contain, can carry a disproportionately huge amount of knowledge in a way that doesn't have a lot of bottlenecks and therefore can be more readily used by these models. So already with very small GNN-style interventions, you can make a big difference in the reasoning capability of the big models that are currently practically used on arbitrary data. So I am generally quite excited about what we can do when we alleviate those bottlenecks for real, especially around long context queries. So TransNar, you should think of it as like the first prototype in hopefully a series of approaches that will try to address this problem. We don't think of TransNar as the exact solution, but we do think of it as something that will hopefully inspire future solutions. Yeah, I would say look out for more of the same. I'm really curious to see what will happen in the future there. That's my opinion, at least. Olga, would you like to say a few words?
Sorry. I will try. Hopefully right now you can hear me correctly. So I'm not much a researcher myself, to be honest. I am a software engineer, and I don't know much about, like, I don't have deep knowledge in this topic. So from my personal perspective, I'm just excited to observe what people in the area will continue to do, what they will achieve. And at the same time, I wish that there will be good engineering practices, that the code will be not painful to work with, that you actually can go to this code base that is mentioned in the paper, and you will be able to launch it, and it will work, and there will be documentation, there will be comments. I just wish everyone to have good engineering kind of day-to-day life. And I hope this will kind of become better, not worse in time.
Yes.
I'm jumping on from Alex's computer, but I think there's a lot of need to understand what like to what extent the models we currently have are capable of performing robust computation. Because to me, it's not super clear. Like I feel like a lot of the work we've done is kind of showing that like at some point things break. And how to fix that, I think, to me, is the most interesting next step. And I think it's not obvious at all. But yeah, that's currently what I'm kind of interested, like this kind of combination of better understanding the failure cases and like kind of pushing forward, given our better understanding what, like essentially improving given our better understanding.
Okay, I hope does sound work now. I think I am still talking through Alex's notebook laptop, right? No. Okay, fine. Yes. Speaking about my perspective, I totally agree with Federico. It's very interesting to find blind spots or weak spots of the model and come up with some architectural solutions, because right now we are very, very restricted in terms of this autoregressive paradigm. Another thing which I find personally very interesting is different, maybe mechanistical alignment techniques, which allows you to understand better what's going on inside of the model. Because right now, despite of having already a pretty solid set of literature about how transformers works, it's still sometimes wander in darkness, because you don't really know what's going on inside. You just feed something and hope that you receive some meaningful answer from the model, and possibly hope that you're capable to, fix it on the fly. I don't think that this approach might be reliable for systems where, like, quality interpretability or interpretability or which decisions are critical. I don't think this is a sufficient level of reliability right now. Over to you, Alex, I guess.
Yes. Okay, I'm back. Yeah. I think we have ultimate and very interesting goal to kind of solve out of distribution reasoning. And as Federica Evaristo said, we definitely need much better understanding of limitations and of architecture. So we do know that small things, perceivably positional encoding or tokenization of stuff like this sometimes makes significant difference. I don't believe that such incremental solutions will lead us all the way. So I would envision really envision somehow hybrid architecture which lets us which would be very powerful in terms of reasoning, but very powerful in terms of pattern matching. And I also would love to see all this system would be tightly integrated and maybe elegantly. So the TransNar is a great system, but yeah, it maybe maybe it can be made simpler and at the same time more powerful. So I do believe that there is still a lot of work and a lot of interest in research in this area. Thank you.
And Wilfred, do you want to add your opinion on this?
Any thoughts from Wilfred?
You're muted.
Yeah, sorry. Yeah, I think I mostly share Alex's perspective on this. In that and also I think it also echoes what Federico was saying. We spotted a few pitfalls and fundamental reasons why there are these pitfalls, and we're trying to patch them. But maybe there needs to be some more fundamental architectural changes that needs to happen in order to not like it would be good. It would be great if maybe models were built in a more principled way, so that we actually know, for example, discovering pitfalls post hoc is a bit it would have been great to have a theoretical like if we build models from theory, then we will have better understandings of what they can do earlier in the process, I guess. And like more related to what we have been working on, I'm very excited about efforts like what we did with the TransNar, because I think I think it's a more principled way of bringing robust reasoning abilities. I mean, as opposed to patching stuff by bringing more quality data, because it's you're really borrowing stronger capabilities, like and from models that have been shown to be better aligned for reasoning. And so for me, that is a better guarantee, like provides more guarantee than trying to build better data mixtures and so on. So I would really like to see these kind of ideas maybe like being more investigated, and also being applied more widely than on than the CRS text dataset, which I think is, I mean, obviously great starting point, but it would be great to like see how to deploy these ideas on datasets where the concept of an accompanying graph or like a problem defining graph is not so clear. And obviously this is challenging, because how do you do that? But that could open more as I was saying, more principled ways of like yeah, more reasoning aligned language models essentially, and also just be cost effective in the long run, because apparently the way reasoning is pursued is it's not particularly cost effective. Yeah, people are scaling compute not just the training time, but also now inference time. Maybe we could circumvent all that. Maybe we don't need that with better models. Maybe we wouldn't need all those things. Yeah.
That's awesome. All right, great. So thank you all for giving those great answers. I'm actually particularly happy that Olga called out the engineering standards in the current code bases, which I think you can definitely tell the difference when you want to make something principled of a code base which is easy to work with versus one which isn't easy to work with. And we're trying to play our part as much as possible in upholding those standards. CLRS itself is a really huge library, machine learning benchmark speaking terms at least. And we're trying our best to make it accessible. We always receive a lot of feedback that's very useful. And I guess we would use this opportunity to say, if anything we said today inspires you to try out CLRS or one of its variants, and you have any hiccups, even if you manage to do what it is you wanted to do, to just please let us know. Like, we're always on the lookout to make the benchmark more accessible and more easy to use for more and more people.
Yeah, I think there's plenty of things to do right, both from an engineering point of view, from an algorithmic point of view, and also from a task design point of view. So thank you very much for your opinions on this. Maybe one very quick final question, like you don't need to do a round of answers. Maybe like yeah, if you feel you can just answer by yourself, or otherwise I'm very happy to hear multiple point of views. But like regarding the use of more, let's say, wise architecture, or regarding the proposal of new architectures that are better aligned, let's say, with reasoning or with the inductive bias that you aim at achieving for your task. Where do you see like the prior human knowledge that we have about the task? Because like a very frequent trend in, for example, deep learning is just to, let's say, rely as less as possible on the human knowledge and let the network learn by itself. Where do you stand in this position? So do you think that for NAR, we shall find better ways also to integrate human knowledge, human priors or human constraints, or we just hope the networks to learn those from data?
Honestly, I do think that this is the kind of question where more people will want to answer. I think it's a pretty interesting question. We actually discussed it a little bit in Slack as well. So it's a great question. Thanks for asking it, Steve. I will give my personal point of view, but I think all 6 of us came into this field from different perspectives. So there is a chance that others will vehemently disagree with what I'm about to say. So please feel free to shout if that's the case. But I would say that, first of all, what you say is completely right. So when you look at a lot of the things that we talked about in the tutorial today, they can boil down to understand your problem and then apply your understanding of that problem to design a better architecture, to design a better training data featurization, to design a better, gradient descent regime or training data regime, right? So yeah, and obviously sometimes there's really heavy math involved behind that particular step, but for all intents and purposes, you could summarize it as understand your problem and then use that understanding to do better. I think there are some really cool papers, which we didn't mention today, but they were mentioned in the original NAR tutorial 2 years ago at LoG, which basically say that that's inevitable if you want out-of-distribution generalization. So I'm referring to some previous works from Bruno Ribeiro's group with Beatrice Bevilacqua and others talking about size generalization, basically saying that in order to generalize, you need a causal model of your test data. Right? Now, in the extreme, this is a causal model of your test data, but if you want to say generalization to arbitrary test data, then this translates to some causal assumption about either the structure of the task or the structure of your model, or more often than not, both, right? So I would say it's inevitable. Now, obviously, we are not just keen to solve the algorithmic challenge. Remember, at the beginning, I motivated all of this by saying we want the architectures to be a bit closer to algorithmic computations, but we don't want them to become algorithms. There are many reasons why algorithms are limited, and we don't want the models to inherit those limitations. Rather, we want them to take the good parts of algorithms while not losing what makes them good in handling various kinds of generic noisy data. So what I would say NAR is all about, and where I stand in this area, is we are basically treading this interesting line between models becoming more specialized for the task versus models becoming more general. And we actually believe, like our ethos is that there exists a sweet spot where the model is just specialized enough to be like maybe hugely more beneficial with the same number of training data points you have for your problem, while still being general enough to be applicable maybe on general language problems or something like this, which is where TransNar, for example, comes in. So we believe that there is a sweet spot, and that sweet spot is not discovered with just simple transformers. In fact, when you think about it, transformers already incorporate some symmetries, like there's explicit object boundaries, attention is inspired by key query mechanisms. In fact, this kind of content-based attention was covered by neural Turing machines, which predate transformers by 2 years. So, computer science-inspired priors have made their way into all architectures, including the transformer itself. And therefore, why would this be the global optimum, right? Why can't we improve some things a little bit more while staying generic? And one good example of this was our asynchronous algorithmic alignment paper with Andrew, Razvan, and Tamara, where, as I've described it briefly in the tutorial, we basically build an architecture that's asynchronous to invariant execution order. That's invariant to asynchronous execution order, while still being synchronous itself. So it still runs on a scalable GPU or TPU, but you have this very nice symmetry property that otherwise it wouldn't be satisfied. So I'd say that's, for the most part, what I would say the philosophy should be in the field. But I would like to see if my co-presenters feel the same way. Maybe I'll prompt Federico to speak first.
Yeah, I agree. I think the sweet spot is like a good. I mean, what came to mind is like maybe this strange analogy where it's like, if I'm building cars and I want a car that can do, like, it can both like maybe move heavy objects and go kind of fast, I build like a pickup truck. But if I just want to make a car that's very fast, I make like a Formula One car. And if I want to make a car that moves heavy objects, I make like a tractor. So like in the sense of like very specialized things, I'm assuming would just work better for the things they're designed to do. But like I view these kind of things as kind of orthogonal. Like you can either go in the direction of like you want to make some hyper specialized system that's very good at doing algorithmic reasoning, or you can kind of try to go in the other direction, just make a very generally nice car. And so, yeah, I think the two views are kind of complementary, but it makes sense that like your pickup truck will never be as fast as a Formula One car, but your Formula One car will never be good off-road. So yeah, it's probably just a game of trade-offs, I guess, as you were saying.
Any thoughts from anybody else from the team? Go ahead.
I think like there may be a Pareto front. We still don't want to build like 1,000 different car models, and like that definitely like even like I don't remember like in reinforcement learning times, if you do take environments which are very far apart, it's hard to make system work both. But there are a lot of similar environments. They like benefit in fact because you like apply something from one to another. Like in the end, you get better performance. And the like better we understand the system, the better we understand limitation. I think this kind of spheres becoming bigger and bigger. So like yeah, it's probably impossible to build the universal system, but like you definitely like converge maybe to certain optimals which can cover huge areas of like expertise. Like so, I still believe that like. We can do better. So like transform is great model, but for certain problems, I think we still need to do better. And I think even all this work with tools usage, like I don't know, like LLMs, calling like APIs. So it definitely shows that like the demand and there exist problems which you want to solve. And like there are definitely different ways of doing this, but I think having great understanding of like neural architectures and trying to find optimal one, I think is very interesting and very promising direction in general.
Yeah, very interesting, very interesting. Somebody else wanna give an opinion? Or
yeah, does anyone else want to speak? Larissa, Wilfred, any thoughts? Or are you just happy with how we've described the entire field? Okay, Larissa's pretty happy.
yeah, please. Okay,
Right.
so I think that we can end it here and leave a 10 minutes break before the next session of orals, so that also the audience can relax a bit their legs and grab a cup of coffee or a snack. I will personally go for a snack now. I want to thank you very much again, all the speakers, for their very insightful and very interesting tutorial. I hope also that the audience enjoyed it, and I will say see you in 10 minutes from now, better 9 minutes from now, for the next session of orals. Thank you all again.
Thank you so much, everyone. Hope you enjoyed it.
Okay, I guess. Let us hope this speaker joins at some point. Ramon Dian Natalo Kaluarachi. I will not attempt to pronounce this name when announcing the paper. Oh, Nicolas Kerriven, I assume is this. Well, let me just make you co-host in any case. So my notion was that decomposing force fields as flows on graphs is the first paper that we're having now. But maybe that's
okay. Maybe I'm wrong. Sorry.
No.
I thought it was gradient scarcity stuff. I mean the.
Yes, it's gradient scarcity.
So that is me.
Well, this is great because Nicolas I can actually pronounce.
Well, you have my talk to train for the other one to practice.
Cool. Okay. Have you been enjoying further sessions of the of this event? What's it called? LoG conference.
Me?
Yeah.
Yeah. I mean, there was the poster session on Wednesday. Yesterday I couldn't, but today we had the Paris local meetup, so I was there.
Nice.
Yeah. Very nice.
Is Alexandra still organizing that one?
Yeah, with several of us. I was also co-organizer. It was in Telecom Town. It was really cool.
Cool. Huh. That's yeah, I mean Paris now has a whole bunch of people or what means now, always had a whole bunch of people in this area. Yeah.
I wanted to add to make sure to send us some pictures from the meetup so that we can collect a very nice portfolio of meetup pictures. So
oh yeah, I know
especially
some of the
most funny
organizers took some. Maybe there are some already over Twitter. I'm not sure. But yeah, I'll pass the message definitely if they are not here at the session.
I think probably the local meetups are the nicest part of LoG conference now.
Both, I would say both. I like seeing it's a nice combination of in person and seeing people from afar as well.
Yeah. Let's see what the in-person version next year brings to the table.
That's for sure. I definitely hope that local meetups will still happen, even though the main conference is in person, because I mean, not everyone is able to go far.
Yeah,
that's kind of the. I would be very much against abolishing the local meetups because I think that's kind of the point of LoG to be accessible to everyone. Okay, but then Steve, do you think we should get started with the oral or what's your take?
Maybe we can try to wait 1 more minute. I just made an announcement on Slack. Let's see if we manage to catch some more people, and then I think we can start. What do you think?
Do you want me to start screen sharing to test stuff, or?
That won't hurt.
Okay, let's do that. I'll share the whole screen. It's usually safer. Yeah, is it good that way if I go full screen like this?
Yep, we can see the whole screen. It's just at the top. We have the black bar of the floating meeting console, but
I'm always
yeah, you can press hide here if you want, but it doesn't really matter.
Where is it? I'm always do you see the hide button?
No, the menu that you just opened that
Oh,
contains
yeah, okay. It was in the menu.
hide video panel. Well,
No,
maybe it
it's
doesn't
hiding
work.
something else. And
Whatever.
I think if I just don't interact with it, it's going to disappear.
Yeah, and I mean it's in the black area of your slides anyway, so who cares? Yeah. But then
Okay, so 5 years later, we still don't know how to use it, but whatever.
I mean, if you're a computer scientist, then it's fine. Then you don't need to know this stuff. Anyway, I think Steve, interrupt me if we should. Oh, and by the way, we literally none of your slides are obstructed by this bar.
No. But I mean,
Yeah.
I prefer not to touch anything, and
Yeah. But then I would say let's get started, if that's reasonable. And with that, I mean, I don't really have much to say, except for we are starting the orals now, Friends of the Sun, and I hope we're all excited about them. And the first one will be by Nicolas Kervin, who I'm sure we've heard that name a bunch of times if we're here in the let's say learning on graph area, and I'm sure he can tell you a lot more about his paper than just the title, which I'm now saying, the gradient scarcity with bilevel optimization for graph learning. But then just let's go, Nicolas. What's the deal?
Yeah. Okay. Well, thanks a lot. So thanks a lot to the organizer for this wonderful conference, and especially this was a paper on the TMLR tracks, which is new this year, I think, which I think is a really a wonderful idea. So this work is mostly the work of my former student Ghanem, but he couldn't be here today, so I'm really presenting on his behalf. But this is his work. So yeah, this work about gradient scarcity with bilevel optimization and graph learning. We'll see briefly what this means. Okay, just to check the time. Okay, so we all know what we're doing here. Here we're looking at transductive semi-supervised learning. So very simple, one of the most basic tasks that we all do when learning on graph. You have a graph, you have a bunch of nodes, V, and within these nodes, you have a subset of labeled nodes that I call V training. And they have the labels, and you want to predict the other labels. So before GNN, one of the most classical way of doing that was to do what is called Laplacian regularization, in the sense that we were directly looking for the labels of the non-labeled nodes by optimizing over this vector here directly of the label, such that you compose your cost function with the cost function over the training labels with some cost L here, so regression, classification, whatever. And you added some regularization such that the predicted label were smooth over the graph. This was under some kind of homophilic assumption over the graph. And what is nice is usually, especially when you do regression, this type of thing is very nice to solve. And it has a closed form expression and so on and so on. That involves the Laplacian of the graph, D minus A, the classical Laplacian, because this guy is just vector of labels computed against the Laplacian of the graph. Now we all know that the modern way of doing that is rather computing some parametric model, a GNN. So here I will consider classical message spacing GNN such that at each layer, a node communicates only with its neighbor. But the message spacing can be anything. It really doesn't matter for the rest of the talk here. It's just a message spacing GNN. So that's, the prediction here will be that you optimize the GNN on the training labels, and you get the best possible weight for this GNN, and that's how you predict your whole vector of labels. Okay. So note here that I have emphasized the dependency on this predicted label on the adjacency matrix of the graph A. And you guessed it's because we're going to do graph learning such that this A will actually change over time with some optimization formula. Okay. So graph learning is now a well-established field in some sense, even though it's very active and there are still many questions that are under scrutiny, including the one that I'm presenting today. It comes from the observation that the graph that you observe, usually the adjacency matrix, is noisy in some sense. You can have missing links, you can have spurious links. Stuff can be homophilic, heterophilic, and so on and so on. And so there are many methods to do graph learning, which graph learning here means I'm going to modify the underlying graph to do my prediction with Laplacian or GNN. Okay, so many ways of doing that. It can be supervised, unsupervised with some, some prior that you're going to put on your graph. It can be differentiable, or it can be purely discrete algorithm on the graph, such that it's better in some way. And here in this talk, as in the title, I'm going to define it as a bi-level optimization problem. So I'm going to see in a minute just why. Okay, so assuming supervised bi-level. So it's supervised, assuming that you have another set of label nodes, V out. So out here refers to the outer optimization problem. So the first one was the inner optimization problem. Here's the outer optimization problem. So just another set of label nodes. If you have only one of them, you divide it between training and validation, as we do usually, and you call V out your validation set somehow, right? You're going to optimize this time over the graph, so over the adjacency matrix, a cost function that is a prediction of this, over these new training labels, right? And here the key point is that this cost function, it includes as a term already the predicted label with respect to this adjacency matrix. That's why it's a bi-level optimization problem, because this prediction usually involves itself an optimization. So if you remember, in the first slide, I optimized the GNN to predict this Y with respect to A. And here I'm optimizing over A, and this has as a term the optimal label that I'm considering with respect to A. So here in this talk, it can be either the GNN or even the simple classical Laplacian regularization. Okay. So of course, you guessed it that it's usually a bad idea to directly optimize over A as a full dense matrix. So what we're going to do is usually restrict this set of learnable graph. It can be more or less complicated. We'll see in the next slide. And one way of seeing that is that, of course, complete graphs are too costly. That's for sure. But also, when you use complete graph, they are very, very prone to overfitting. And you can even show very simply that if you optimize over the complete graph and you can learn any edges on anything, well, then it's going to discard a lot of edge where you don't have labels. Okay, and this is a bit related to gradient scarcity and what we're going to see just after. You can also add some regularization. It's usually a good idea. Again, for the same idea, that you want to fight overfitting if you learn all the edges of the graph. So a few remarks. It's this graph learning problem was often formulated as a joint optimization problem over the labels and the graph. So a min-min, right? You minimize over the graph and the labels in the same cost function. This is a marginal idea. All the joint optimization can always be formulated very simply as a bi-level optimization with just min-min. It's a bi-level optimization. But all the bi-level optimization is not always a joint optimization, especially when the cost functions are different and the inner optimization problem is something a bit complicated, non-convex, like learning a GNN, for instance. And when you do it in practice, if the inner optimization problem requires itself, in practice, I mean, in the code, requires backpropagation, like learning a GNN, then optimizing this outer cost function will require to backpropagate through the backpropagation, so what is called higher order backpropagation. If you've never seen the term, they are dedicating a PyTorch library to do higher order backpropagation. So backpropagating through backpropagation. Okay, so just a few minutes on what I can choose for this problem. So I'm not going to do the whole field here, but usually what we can choose for the set of matrix that you want to learn. Again, I said to you that the complete graph is not a good idea. You may want to learn just the weight of existing edge. So you observe some edge and you optimize over the weight of the existing edge. So it has a few names. Usually it's called edge refinement or edge weight learning on this type of thing. it may be a good idea to add some new edge in case the edge that you observe there are some missing links. So a compromise between the existing the observed graph and the complete graph is to learn edges up to k hop or r hop here of the observed adjacency matrix. Sorry, I'm a bit sick, that's why. So you learn the weight of the existing edge, but you also learn new weights between nodes that are 2 hops or 3 hops from each other. It can be a good idea to add a few shortcuts in the graph. It's also a good idea to add regularization. There are many choices for this. And usually, you guessed it, the modern way of learning a graph is to do itself a parametric model and optimize over the parameter of this parametric model. So it's some type of graph-to-graph GNN. It computes some kind of node embedding, for instance, and then predict edges with an MLP that takes the node embedding as an input. It's usually the modern way of doing graph learning. But to do some theoretical analysis, especially gradient scarcity, so I'm going to explain what is gradient scarcity, consider edge refinement. So we just want to learn the edge weight of the existing graph, right? So if you take as a prediction model a GNN with k layer, I'll start with GNN here because Laplacian regularization is actually more complicated for what I want to say. If you take as a model a GNN with k layer, then you can see that it has a finite receptive field of size k, since it's a message passing GNN. And as such, the edges that are more than k hop from the training nodes do not play any role. This is something very known, that they don't appear in the cost function. I see that it's very known when you optimize, when you want to predict labels. You know that some edges were not going to be taken into account just at inference, but not for training. But when you optimize over the graph, this is a problem, because when you optimize over the graph, these edges are trained somehow. You compute the gradients and they are trained. And gradient scarcity refers to the fact that from this very simple fact, if you consider the edges that are more than k hop away from the training nodes, k hop in terms of shortest path, right? Then the gradients of this outer cost function that is supposed to learn the graph will be exactly 0 with respect to these edges. So they will receive no gradients ever. And this is a problem. This is what is called gradient scarcity. So it was known for joint optimization. So in this paper, we prove it for bilevel optimization. The proof is essentially the same. It's a bit more complicated because you have some stuff that were 0 before that are not 0, but everything cancels out and you still have gradient scarcity without surprise, as expected for bilevel optimization. Okay. So you have many ways of counteracting gradient scarcity. I'm not going to go over them here, but I'm just going to talk a bit about Laplacian regularization. So if you don't know it, but if you know it, I'm telling that to you now. Laplacian regularization, unlike GNN, has an infinite receptive field. So the whole graph usually comes into account when you compute the Laplacian regularization here, when you predict the labels. So do we have gradient scarcity in this case? It wasn't really clear because unlike GNN, it's not a strong size k receptive field. Well, yes, in some sense. Yes, in some sense, because you can compute some eigenvalues of some matrix. I'm passing the detail here. But what you're going to get is that the gradients of the edges that are far from the training nodes decrease exponentially with the distance to the training nodes. Okay, so it's not exactly 0 as before, like you had for GNN, but they decrease exponentially, and it can go very pretty far. Okay. How am I doing on time? Okay. So what's interesting is that the eigenvalue of this matrix that determines the rate of decrease is a bit linked to the distribution of the training nodes and its relationship with the frequency of the Laplacian. So I'm not giving you details here, but basically you can say that if the training nodes are very low frequency, very grouped together, then the decrease is going to be slower, but then you're going to have like big distances in your graph from the training set because it's grouped, it's isolated from the rest. And if it's more aligned with the high frequency of the Laplacian, then the decrease is going to be very fast. But that, since it's well spread, the distance to the training set is usually, of course, you can find counterexample, but it's usually much less. So you have this kind of trade-off that is raise a lot of open questions that we don't have answer to yet, but it's interesting because this is something we don't really talk a lot, like the distribution of the training nodes within some graph and within the graph. Okay, so from all the ways that I showed you before, there are some ways to mitigate gradient scarcity. Of course, I was only talking about edge refinements over the existing graph. We're not going to go over all the details, and I'm not proposing any new method to mitigate gradient scarcity. There are more than enough already. What's one interesting thing that we observe is that whatever the method that you choose to mitigate gradient scarcity, regularization, or learning a graph-to-graph GNN, I mean, everything else apart from edge refinement, it's graph learning over small graph like Cora, CiteSeer, PubMed, I mean, medium-sized graph. It's a lot subject to overfitting. You can see here in the table of results, we managed to do better testing than simple prediction over the observed graph, but you still have a gap between the training test, and at least in our experiment, graph learning, if you're not careful, it leads a lot to overfitting because you learn the edge between the training nodes and everyone is happy and they don't care about the testing nodes. So yeah, the more parameters that you have, of course, more overfitting if you're not a bit careful. Okay, so I'm going to stop here to conclude. This was a simple work, but it raises some interesting question about graph learning, gradient scarcity, and the distribution of the training sets within the graph and its relationship with the graph topology, which is a topic that I find is not often discussed, but has some interesting theoretical consequences. And I'm just ending my talk by saying that I recently got a grant to work on theoretical graph machine learning. So if you know any students, we'll be happy to come to Rennes, the beautiful city of Rennes, eating crepes and stuff. Don't hesitate to send me a message. Thank you.
I was muted, but yeah, that's great. I think eating crepes, that's something to do. As it happens, I'm making crepes for the Thanksgiving weekend tomorrow, and
Nice.
can only support that. But then, so the next speaker, I think we would welcome having him here or them here. So if you're around, just shoot me a message in the chat because I cannot find you. Yeah, because next we would like to talk about towards a GNN framework for combinatorial optimization problems. I see Frederick Wenkel. There we go. Make co-host. So Frederick, I made you a co-host now, which means that you can start screen sharing and doing deeds like that. Hello. And with that, Nicolas, thanks for the nice talk. And
thank you.
I'm sure someone might reach out about those grants and working with you. That's super cool. Oh, and about the crabs, of course. That's important as well. But with that, thanks, Nicolas. And
thanks a lot.
Let's move on to the next one with Frederick. And yeah, are you all set? Do you quickly want to say something so we can see how well we can hear you?
Hello. Yeah, can you hear us?
Yeah, that works very well. But
great.
Then,
yeah, I will be presenting together with my first author, Sammy. And yes, so I hope everything is fine. And then in that case, we will start. Like, I think our talk was scheduled in 10 minutes, but we can already start, I guess.
Yeah, I mean, fine by us.
Absolutely. Let's go.
Right.
Okay, so today we're going to present our latest work towards a general recipe for combinatorial optimization with multi-filtered GNNs. Fred and I are going to present this together, but we would like to take the opportunity to thank our co-authors here, Stefan Horoi, Michael Perlmutter, and Guy Wolf, of course. Okay, so let's get started. So many of us in the audience will be, to a different extent, be familiar with combinatorial optimization, but for the sake of completeness, let's do a very quick overview here. So in combinatorial optimization, we're trying to find an optimal subset of objects from a finite set. And in this context, we're going to think about combinatorial optimization over graphs, which is like a very common case. where the subsets are graph nodes. They could be edges of the graph or paths over the graph, but basically some subset of the graph object. And there are many instantiations of combinatorial optimization on graphs, like the most popular ones among many others being max clique, maximum cut, minimum dominating set, and perhaps the even more well-known traveling salesman problem. And then there are also other variants like vehicle routing, graph coloring, etc. So like we're talking about a very large family of problems here. The thing is, most of these combinatorial optimization problems are NP hard or NP complete. So especially when you scale your graphs to about, let's say, tens of thousands or hundreds of thousands of nodes, generating exact solutions with conventional tools like MIP programming, like let's say using the Groby solver, these types of things can be prohibitively expensive. So that's where deep learning comes in, because with deep learning, the idea is that let's generate approximate solutions more efficiently. Let's just do a forward pass, let's say, across a neural network and just get certain predictions. And supervised or unsupervised, as in self-supervised methods, as well as reinforcement learning approaches are all viable. Many of them have been tried and have been successful to different extents. And since we're talking about combinatorial optimization on graphs here, obviously GNNs emerge as like a natural candidate, but conventional GNNs typically assume that like your information is very local and like treats essentially graph smoothing as an inductive bias. What we know for a fact is that this is not an assumption that always works well for combinatorial optimization, where you also need high frequency information depending on the task at hand. We're going to explore this in more depth in real soon. So let's look at a few problems that we mentioned in the previous slide. So in the maximum cut problem, you have your vertex set, and then you want to partition this vertex set into two subsets such that you maximize the edges that connect nodes from different sets. That's the idea. So you want to get a cut with as many edges as possible. In the maximum clique problem, you want to find the largest node subset that is fully connected, which is by definition a clique. So you want to find the maximum clique, essentially. And in the minimum dominating set, you want to find the smallest subset of nodes such that every node in the whole graph is either within this subset or is neighboring this subset. So in the sense of like, you can think of it as from a GNN perspective, if you just diffuse, do a one-step diffusion over the graph, over the MDS, you can reach every node in the graph. That's the main idea in MDS. Okay, so I'm going to pass the torch to Fred, who's going to take us through the methodology we employ here.
Thanks, Sammy. So yeah, talking about the methodology, we have here an input graph to our pipeline, which is then equipped with intrinsic node features. Those encode the structure of the surrounding area about a node. It could be, for example, the node degree, the clustering coefficient, or the eccentricity. This information goes through an MLP decoder, which then feeds into our multi-filter GNN. The output of this GNN is on the node level, and we feed it through an MLP decoder together with a sigmod. So the output of our learned of the learned part of our pipeline is a vector, which we can see as a probability vector that gives us for every node a probability to be part of the solution. Looking here for into the case of the maximum cut problem, we then have an unsupervised loss function that we use for training. And what we can think here of the probabilities is that, yeah, we want to bipartition our node subset here so that we cut as many edges as possible as we move between the different classes. And the probability for every node will tell us if it's smaller than 0.5, then we want to have it in the first part of the partition. If it's bigger than 0.5, we will move it to the second part of the partition. How can we train with that? So the first step is that we apply the transform 2p minus 1 to our output vector. That means that we move our values from the interval 0, 1 to the interval plus minus 1. And what this quadratic form then does is that we will sum over all the edges, and we will get a negative contribution to our loss if the two nodes that are connected through the edge have a different sign or are in different parts of the partition, and we will have a positive contribution to our loss if they have the same sign. This is the learned part of the pipeline here, and once we have learned these probabilities, we can pass them through a rule-based decoder where we can simply separate the nodes of our graph according to the sign of 2p minus 1. Similarly, we also have an unsupervised loss function to train this model for the maximum clique problem. And here, our loss function acts as a surrogate to the true objective of the maximum clique problem. So you can see this here on the bottom here. The true objective function can be seen as like assuming that we know all the cliques in our graph, we could just, for each of the cliques, see how many edges the clique contains, and then pick the one with the most. So, and this translates to our surrogate loss function that the first loss term encourages the model to push probabilities to nodes that are within the clique, while the second loss term encourages that nodes with high probability are highly connected. So, and together, these two, this loss function then approximates the true objective of the maximum cut problem. To decode a solution from this, we will order then the nodes of our graph according to decreasing probability. We will instantiate our solution as the highest probability node, and then subsequently add nodes to that set according to decreasing probability, and every time check if we are still within the clique. Lastly, for the minimum dominating set problem, here we want to find a minimum set so that every node of the graph is at most one step away from that set. So again, we have a two-term loss function where the first part, the L1 norm of the probability vector, enforces sparsity. So that encourages the model to have the least nodes possible in the solution set. While at the second loss term makes sure that next to every node of our graph, we have at least one node with high probability next to it. And the decoder will function very similarly as for maximum clique, that we again order our nodes according to decreasing probability, and then step by step construct a solution by going through the nodes by decreasing probability. So what's interesting about this is that all these problems are NP hard, so it's prohibitively difficult to get enough ground truth solutions for supervised training. But the nice thing is that our unsupervised loss functions allow us to train these models without access to even a single ground truth solution. The second nice thing is that our rule-based decoders are constraint preserving. That means that even though we cannot guarantee that the solution of our model will be the optimal solution, we can always be certain that it will satisfy the constraints. For instance, the solution, our approximation for the maximum cut, we can make sure that it is a maximum, it is a clique, although we can't guarantee that's the maximum clique. And similarly for the minimum dominating set, the solution we propose will be a dominating set, although it may not be minimal. With that, I will move on to our modeling approach, which is through a multi-filter GNN, where you can see here, for each layer of this model, our input node features will go through different pathways, where each of them can be seen as a separate GNN layer. So the ones we see here are traditional averaging operations, which have different scales of the support matrix. This is the matrix we use for message passing. And for instance, if we take s to the power of 1, this is the most traditional aggregation mechanism, which we know from, for example, GCN and GIN and many others. And we'll just aggregate information around every node from a one-step neighborhood. But we also have like higher orders of the support matrix where we then for S square, we will aggregate from the two-step neighborhood and so on. So even though those are very traditional methods, like each of those channels will give us access to a different receptive field around each node. Then we complement those filters with what we call comparison operations. And those are filters where we replace the support matrix by scattering diffusion wavelets. And those encodes fundamentally different operations compared to what we know from traditional GNNs, because here we have differences of different scales of the support matrix. For instance, the psi1 diffusion wavelet, what we will do here, we will first aggregate around every node from a one-step neighborhood, what we see here on the left. And for S square, we will aggregate from the two-step neighborhood and then take the difference of that. So this diffusion wavelet at every node will compare two neighborhoods of different size. And this carries on to higher order wavelets here, for example, psi2, where the scales of the support matrix are usually powers of 2. So here we will first, we will compare a neighborhood of size 2 around every node to a neighborhood of size 4. The magic of this model is now that how we combine at the node level the information from these different filters, where we have two different attention mechanisms, where at every node, the model can decide to which of the filter responses it wants to attend. And this is very different compared to what we know, for example, as graph attention networks, where we attend to our neighbors at every node. Here it's really that our node can attend to different filter responses. For instance, you can see here at this node that it can choose which information is most important at this node, and this can be different for each of the nodes of the graph. So what this model is capable of doing is to learn very complex local functions that depend on the local node neighborhood, which is very, very helpful for the problems we are dealing with here. Additionally, it's very important to have this decoupled attention mechanism that you see here, that we have an attention mechanism for the averaging operations versus the comparison operations. And we show theoretically in our paper how this is an upgrade compared to former architectures, which had just a single attention mechanism that throws together all the filter responses at the same time. And we show that in such cases, the filter responses of the averaging operations will always outweigh those of the comparison operations and limit the expressivity of the model. And with that, we move forward to the empirical results with Sammy.
All right. So before we actually look at the results, what are our baselines? What are the tasks and models we're comparing against? So again, we are testing on max cut, max clique, min dominating set, and we ran experiments for a set of small and large graphs. This is going to be relevant in a second, where like the small graphs are about 200 to 300 nodes, and the larger ones are, I believe, 800 to 1,000 nodes each. And so first, we have non-deep learning pipelines like Groby, a general purpose optimizer, and then greedy algorithms, and then mean field annealing algorithms, essentially. And then from there on, the real, like, more comparable baselines we have are ARDOS GNN, which is a seminal GNN from a few years ago by Karalias and Lucas, which is basically a slightly altered GIN that is suitable for combinatorial optimization and like gets good results across several tasks as well. There's the anneal model, which is essentially the ARDOS GNN with some max entropy annealing regularization that helps the optimization process in certain cases. There's the scattering clique, which is a prior work that also leverages these diffusion wavelet based bandpass filters, but with a different mechanism. And finally, we have the GFlow network-based GFN. That is like a paper from last year, I believe, which proved to be quite successful across these tasks as well, while like the caveat being that it's much more computationally expensive to train and run inference on. So we see that in our results, GCon is the best self-supervised learning method on both MaxCut and MDS overall for large graphs, but also on the smaller ones. Whereas in MaxClick, we're pretty much on par with GFN, though GFN like proves to be slightly better. But overall, we're either like the best method or the second best, essentially. So, which kind of is in line with our aim that we want to arrive at a model that is consistently good across a large variety of combinatorial optimization tasks, which may require different inductive biases than just, low pass filtering, graph signal processing perspective. And what's more is like GCon, while being so successful, has similar scalability properties to other MPNNs like ArDOS-GNN, which makes it much faster to both train and test compared to methods like the GFlowNet based solver. And like it's much more faster than say the Groby solver. And the bottleneck here is not the inference pass of the GNN, but rather the decoder. And when your decoder is very fast, which our implementation is for the MaxCut, we not only beat like a time budgeted Groby, but we also gain like a 130 times speed up on MaxCut compared to Groby. So I think to run this on these large graphs, 500 of them, it took us about like half a minute, where for Groby, it's more than an hour, like just to put it in context. And we see that like these decoupling of low and high pass filter is very essential for MaxCut and MDS. Whereas MaxClick tasks seem to rely more on low pass information, essentially. But overall, we have arrived at a network that can pick and choose the types of information it may want to focus on at a node-by-node basis, as well as depending on the task. So we arrive at something that's very flexible. Finally, we run some generalization experiments, and we see that GCon is actually quite adept at generalizing across graph sizes. So in the table, you see we run two types of generalization experiments. Like I mentioned, we have small and large data sets for each task. So we're testing, okay, like what happens if we train on the small data set and try to extrapolate to the large ones. And basically the percentage differences are here you see are what's the difference, what's the percentage drop you see when you train on, say, a small and test on the large compared to just training and testing on the large graphs. And overall, we have less than 6% performance drop, which when you put it into perspective, like the overall how much better GCon was doing, for example, compared to standard message passing neural network-based methods, we see that GCon can outperform in distribution GNN methods like ArDOS-GNN, even when trained on like graphs on different sizes than it's tested on. We also see that like the GFlowNet is also quite successful in generalization, whereas like ArDOS, ANIL, these types of like conventional GNN-based methods struggle quite a bit, even though like the variance per task changes a lot. So, okay, what are the main takeaways we have here? Perhaps the most important thing to notice is that like conventional GNNs, like the biases associated with conventional GNNs is not really compatible fully with several CO tasks where high frequency information is also relevant. So we need something that can leverage both types. And here we introduce GCon, which leverages, again, these both types of information, making it a powerful architecture for a very large array of CO problems. As we showed, like GCon can outperform both other GNNs as well as GFlowNets and even challenges Groby while retaining like scalability and like the sparsity of a standard GNN method. And finally, we discussed this in more context in the paper, but we see that GCon is the overall framework we presented is extendable to many optimization problems that we don't cover in this paper, including ones that are based on edges or paths, like, say, traveling salesman problem. The only thing you need to do is to introduce a modular loss and decoder that's appropriate for your task, and you can keep the model backbone separate and get close to optimal performance with the GCon framework. So that concludes our presentation, but we're more than happy to take any questions and discuss this in further. Yep.
Awesome. Thank you very much. It seems we do not have any questions in the chat, but we have the QR codes, and yeah, I'm sure people might be happy to check out the paper further and take away some more details. And with that, would you have any last words that you want to say about the paper, or should we call it a day and move on to the next?
I think we're good. I think we covered everything, and yeah, always feel free to reach out to us. We have some ideas about future work as well. So this is probably not the last you hear of this work, but yeah, thanks a lot.
Thank you.
Great. Thank you very much, Friedrich. Thank you. Sorry, I forgot the name. Shin? Do you want to say his name, the name of your co-author?
Frederick and Sammy, and we...
Sammy. Thank you very much. Thank you, Frederick and
You're
Sammy.
welcome.
With that, let's get to the next oral. And I think that is by you. But if not, then whoever else is next, please write me a message so I can make you co-host and you can start screen sharing. But we are also a little bit in front of the schedule, so it might be happening that it might be happening that our third presenter is still taking a little while.
I'm presenting closing remarks. It's not my turn, right?
I thought we had a third,
Okay.
like visiting graph homomorphically, neural incomplete factorization as a third oral.
Okay.
Hausner. We have any? Oh yeah, there's a Paul Hausner here.
Hey, I couldn't send you a message for some reason, but now it seems we're good to go.
Yep. Sorry about that. I might have or should have called your name sooner, but then let's just get straight into it so we get as much time as possible for your presentation.
So sorry. All right. Thank you very much, Hannes. It's very nice to be here. So my name is Paul. I'm a PhD student at Uppsala University in Sweden. And I have the pleasure to talk today about our recent TMLR paper about using graph neural networks in order to learn preconditioners for the conjugate gradient method. That's a topic I've been working on together with my supervisors, Åsa Nökdem from KTH in Stockholm and Jens Sjölund from Uppsala for the last roughly 2 years. But let's take a step back and first talk about sort of learning to optimize. So using machine learning models in order to accelerate the solution methods for numerical optimization problems. And so the idea is that we often have to solve similar problems over and over again, and we can then use sort of the similarity between different optimization problems in order to train a machine learning model. And then later we can amortize the cost of this training of the model and creating of the model by solving many related problems in the future. And sort of this paradigm is also known as learning to learn or meta-learning, when the underlying optimization problem we're considering is actually neural network optimization itself. That's a quite famous paradigm, or also in a more general framework is related to AutoML, where we're interested in learning to optimize general machine learning algorithms. Let's make this a little bit more concrete. So usually we start with a parameterized optimization problem. So we want to minimize some function f with some optimization variables x, and we have sort of some distribution over parameters y. So that is just the context of our optimization problem. So then we assume some unknown probability distribution over these parameters. And our goal is then to learn a machine learning model, G, which takes the parameters and of our optimization problems and some learnable parameters for our optimization and produce sort of either directly the solution to our optimization problem or sort of augment the classical optimization algorithms. And we can then use different kinds of loss functions in order to train this model. So either we can go towards end-to-end learning, or we can use theory in order to inspire our loss functions in order to get a better performance. The ultimate goal is then to solve some optimization problems fast for new parameters that we might obtain in an online fashion. So we're at the Learning to Graphs conference here, right? So it's natural that we might assume that our learning to optimize model will be parameterized with a graph neural network. And here we especially want to highlight sort of the connection between graph neural networks and classical numerical linear algebra methods. So I guess everybody here is familiar with the classic graph neural networks that operate, or the process data that lives on a graph. But just to recap real quick, the classic message passing framework sort of consists of 3 consecutive steps. So in the first step, we sort of compute an edge embedding for every directed edge in our graph based on our old edge features and the adjacent nodes. Then in the next step, we aggregate the adjacent edges for each node using some permutation invariant function. And in the final step, we update the node embeddings. And both of these updates of both edge embeddings and node embeddings are usually implemented using some small fully connected neural networks. And since these neural networks only operate on sort of the building blocks of our graph, a graph neural network can operate on any size of graph, as we've all seen in the previous presentations. So how does linear algebra come in? Well, every matrix A actually corresponds exactly to an adjacency matrix that we can interpret as a graph. Moreover, many both numerical algorithms, but also numerical linear algebra algorithms can be described as a graph problem. And we use this insight in order to construct our GNN architecture later on. And so the optimization problem we're looking at, as the title already says, is the conjugate gradient method. So the conjugate gradient method aims to solve just linear equation systems, AX equal B. So we can also see this as minimizing unconstrained quadratic objective, where both A and B are sort of the parameters of our optimization problem, and X is the optimization variable we want to solve for. And so the conjugate gradient method is a quite famous iterative method to solve these equation systems we obtain, where we assume that our matrix A is square and symmetric and also positive definite. So that means our quadratic objective itself is strongly convex. And the method is especially effective when we have large scale and very sparse problems. So one very common setting where this occurs is in the discretization of finite element methods for partial differential equations. The convergence speed of this method thereby typically depends on the condition number of our matrix A and also the distribution of the eigenvalues of the matrix. So a classical heuristic that's very important for these solvers is finding good preconditioners. So the idea is that we want to find a matrix M, which usually also has to be symmetric and positive definite, and for resource constraints also sparse, that improves the spectral properties of our system. So instead of solving our original system AX equal B, we might solve a different system where we multiply, for example, by the left with our matrix M. And so here we have to make a trade-off between the time spent to compute the preconditioner versus the acceleration we obtain in the conjugate gradient method. So if we use, for example, just the identity matrix as a preconditioner, we obviously don't obtain any speed up since we just recovered the original problem. On the other hand of the spectrum, if we use the inverse matrix itself as a preconditioner, we recover a direct method, so we don't need any additional iterative steps anymore. So usually preconditioners are somewhere in between these two extremes. So the Jacobi method, for example, approximates A using a diagonal matrix, which we then know how to invert. And another class of quite popular algebraic preconditioning techniques are the incomplete factorization preconditioners. So there we start computing a factorization of our matrix A, but do not fill out all the elements of that matrix. And our method is highly inspired by that, by including a neural component into this incomplete factorization. So the idea is to parameterize the learn to optimize model that takes a matrix A and produces a suitable preconditioner. And as I said on my previous slide, we both need symmetric and positive definiteness, as well as sparsity constraints for our preconditioning matrix, for our output of our neural network. So the sparsity constraints I'm going to talk later about. Let's first focus on how we make sure that our preconditioner itself is symmetric and positive definite. So instead of directly mapping to a matrix M, we instead actually map to a lower triangular factor, lambda. And for lower triangular factor, we know exactly how we can make it at least positive definite, and that is exactly by enforcing positiveness on the diagonal elements. And that we can achieve by just using a suitable activation function in our neural network. In order to then re-obtain our preconditioner, we can just multiply the lower triangular matrix together with its transpose, similar to the incomplete Cholesky factorization itself. So, as I said, there's a very strong connection between graph neural networks and matrices. But the problem here is that we cannot actually use the matrix A directly for the message passing. So why is that? So if we would just use A directly for the message passing, the outputs that we get from the network in the terms of edge embeddings are typically non-symmetric anymore, even though we take in a matrix A, which is symmetric. And that is just due to the fact that the edge updates usually take into account both the nodes that the edge is connecting in a directed fashion. The other problem, which is way more severe, is actually that we use a lower triangular part only of the output, and that breaks the permutation equivariance we obtain usually from the neural network. So in the naive framework, we would first use message passing and then use the lower triangular matrix of our message passing output. We instead suggest to first transform our matrix to a lower triangular matrix and use a graph of this lower triangular matrix for our message passing. The problem then becomes that by only using the lower triangular matrix, we basically only let information flow in one direction, and that is from lower order nodes to higher order nodes, where we, in the beginning, fix the node ordering. In order to circumvent that, we first do a step with the lower triangular part of our matrix using message passing, and then the second step, we use the upper triangular part of our message passing using the same edge embeddings for the second step. So now we can obtain a valid factorization of our matrix, which is positive definite. But now we have to achieve that we can also train this factorization in order to resemble a neural incomplete factorization. And so how we phrase this is that we want to minimize the distance between our original matrix A and the learned factorization that we obtain from the neural network, which then we make subject to sparsity constraints. So since we only input edges in the beginning, these are exactly the non-zero elements we obtain in the end in our output matrix. And we can encode here also different types of sparsity constraints. So the ones I've shown here in the upper objective is exactly the ones that doesn't allow any fill-ins. So exactly the elements that are non-zero in our original matrix A will also be non-zero in the learned preconditioner. We can also allow additional fill-ins using some classical heuristics from numerical linear algebra. For example, we can use the sparsity patterns corresponding to A square or using higher order polynomials. It is also possible to then learn actually sparse outputs by adding an L1 penalty term to the objective function itself. So we start with a bigger sparsity pattern, add an L1 penalty to our objective in order to get a sparse output, again, from our graph neural network. But here we of course have to make a trade-off between the time we need to run for the forward pass of our graph neural network and how good the approximation is we get out in the end. So in order to actually allow efficient training, we need to do some additional computational tricks. One key problem here is actually that the Frobenius norm scales computationally quite poorly, since it requires matrix-matrix multiplication. And so for very large-scale matrices, this is extremely costly on one hand, and on the other hand, we need to compute the gradients with respect to these, which then just blows up our memory. So instead, instead of minimizing the Frobenius norm, we propose to instead minimize an unbiased approximation using the Hutchinson trace estimator. So you can just sample a vector with IID Gaussian elements and multiply that with both of our matrices in order to get an approximation of the Frobenius norm that only relies on matrix vector multiplications that we can compute very efficiently. So this allows us to have very efficient training. And then if we look at the difference here on the right-hand side in the figure between using our stochastic approximation as a training objective or Frobenius norm as a training objective, we see that in terms of performance on the validation loss, where we always compute the full Frobenius norm, it is very marginal. During inference, we can also show you that our model is very, very efficient and only requires a linear time complexity in the number of non-zero elements in our matrix. So let's look at some results. So we evaluate our methods on two different synthetic data sets. So these are basically the generating distributions over different problem classes. So one is using random matrices of size 10,000 by 10,000 with approximately 1% non-zero elements in each matrix. And the other problem is motivated by an example I already talked about earlier. It's the Poisson partial differential equation discretized on different two-dimensional domains using the finite element method. And there we test our method on problems from the size 20,000 until 500,000. But here, one key goal is also to show the size generalization of our model. So we only train with problems up to size 150,000 by 150,000. In general, it's however not easy to generate suitable datasets for these problems. And so we have to sort of trade off the difference between the problems within a dataset and the generalization abilities of this model. And so future work is needed in this area in order to address these issues. So these are really most synthetic datasets we're evaluating on here. So for the synthetic dataset, we can see that our learned approach with additional sparsity is around 40% faster than incomplete Cholesky, the fastest other baseline we're testing against. So if you're interested in solving many random matrices, then our method is quite good. So for the partial differential equation data, we can see on the left-hand side, we can see how long it takes to actually compute the preconditioner. So that is just the forward pass through our model. And here we can very nicely see the linear scaling of our model that we also showed theoretically. And compared to incomplete Cholesky, we're significantly faster in computing, so our linear complexity grows with a better rate compared to the baseline method. On the right-hand side, we see the solving time of the actual optimization problem, and there we see that both methods basically scale the same. Then let me give some outlook and future work. So as I said before, right now most of these problems are fairly synthetic. So future work includes that we want to extend these methods to other problems, such as interior point methods and Gaussian processes. We actually have to solve over and over again linear equation systems within these methods. Additionally, we can learn additional heuristics for these preconditioners, like extending the sparsity pattern and learning the sparsity pattern directly, or additionally learning the reordering of the matrix in the forward pass. In our forthcoming paper that's going to be presented at the Northern Lights Conference in the beginning of next year, we've also extended the learned preconditioning to other iterative schemes, such as GMREST, and have improved the training objective and shown its connection to large and small singular values. So development of data-driven preconditioning really has just begun. And the story doesn't end at only linear equation systems. Preconditioners can be important for any type of optimization problem. So let's give me a quick summary. So heuristics such as preconditioners and optimization algorithms can be replaced by data-driven approaches, as we've shown in this paper. And preconditioning is a very natural form for learning to optimize, since it can be applied to all kinds of different optimization problems. And maybe most interesting for the graph community is that graph neural networks are extremely natural computational backend for numerical linear algebra. So there's a lot of different things we can use graph neural networks for in order to improve actually the linear algebra side and exploit sort of this connection between GNNs and matrices in order to speed up optimization problems. Yeah, thank you, and I'm happy to take any questions.
No, the thanks is from us, Paul. This is excellent. An awesome finish to this conference, I think, with this last oral session. And yeah, this I think marks the end of the deal, except for Hugh's closing remarks. And let's get to those. And I'm pretty sure we're going to hear some exciting stuff there, like some news. Hugh, are you announcing some things? Is that right?
Yeah, thank you.
Okay.
Let me share my.
Like the reviewer awards, did we already announce those?
Yeah, we haven't. I'll be announcing the awards for
Well, then that's pretty exciting. Who gets the money? So let's see. Of course, we're grateful for any reviews, but there are some especially highlight-worthy reviews, and they should be rewarded. But then
Yes.
let's go.
Exactly. Thank you so much. So thank you everyone for attending the Learning on Graphs conference this year. And here comes to an end of our conference, and I'll be presenting the closing remarks and presenting the awards for the best paper, top ACs, and top reviewers. So just to recap, the Learning on Graph conference was established with the core ideas to present the latest advances in graph and geometric ML. And we are a community-driven conference, and we want to build a community that is truly accessible to all by making the conference free to attend and in a virtual format. We also emphasize local meetups where the researchers in in graph ML can meet up locally around the globe. We also focus on review quality by providing monetary rewards to the top reviewers as an incentive to improve the review quality. So this year's program spans over 4 days, and we had 4 keynote speakers, 5 tutorials, 12 orals, and 2 poster sessions with 16 local meetups. And we are truly thankful for everyone participating in our conference, presenting their research in graph ML that spans such a large and wide